To see you all here in person and also people online. I will start right away with our overview, and then we'll go through the session talks. And we do have some discussion before the break today and also before the end of the session. So just to keep that in mind for questions. So my name is Simone Tilmes. I'm the co-chair of the Chemistry Climate Working Group. We also have Rafa here visiting as the outside co-chair. We have Rebecca Buchholz as our liaison, as well as Sean Homikel, who is online, and Francis Fitt is our software engineer. And so I want to give an overview of the recent work we have done in our working group, as well as especially with some focus on CESM development, CSM3 developments. And so starting with reminding you of different chemical mechanism. So what you see on the left is the number of components, so tracers in the chemical mechanism, and those scale directly with the costs. So we do have in the past our TSMLT chemical mechanism, the troposphere, stratosphere, mesosphere, lower thermosphere chemistry. That was the most complete one for the WACCM model. And then we had our T as one mechanism, that's the troposphere, stratosphere mechanism 1. But now for CSM3, we change our naming convention a little bit, and you will also see that in the new COM sets that will come up. We'll have a number for the tropospheric mechanisms, because those are mostly changing, while the stratospheric mechanism and middle atmosphere mechanism hasn't been changed. So we call, say, the TSMLT mechanism with the T1 MA, so T1 middle atmosphere mechanism in the new versions, and then we have T1, T2, T3, T4, T5. I'll go a little bit more into the details. For the especially production experiments that may be planned for CMIP7, and also for climate simulations, longer simulation, we now have the T4S mechanism, which is a bit of a cheaper mechanism in the troposphere, less hydrocarbon reactions and species, which actually reduces the performance by about 30, so the computer cost by about 30%, which is helpful. Then we have a specified oxidants and greenhouse gas mechanisms, really simplified troposphere chemistry to serve for production of aerosols in the troposphere and prescribed chemistry in the stratosphere. And so just another overview in terms of the model. To remind people, we have the WACCM model that is still the 140-kilometer model. We call it also the high-top model. And now the workforce for future simulation and what we're discussing on all these meetings here is really the mid-top model, 93-level model. And then there's also a low-top model version for other applications. And depending really on your science questions, you can have very different chemistry with it. Like for WACCM, you can have that full chemistry, but also just the middle atmosphere chemistry with simplified troposphere chemistry, or fully prescribed chemistry for dynamical studies. And for the tropospheric mechanism, you see here a few that I already described. Just some details also on our air quality. Sorry, I wanted to point. Our air quality chemistry, so really the more comprehensive mechanisms are the T1, T2, and T3 mechanism. But then also what you will hear about a bit today is the T5 as the halogen chemistry. Short-lived halogens are included as that will also serve better for chemistry. And we do have different aerosol schemes. We have Karma integrated in CSM development version now, and Mosaic may be integrated in the future. So if you have any questions on that. I do want to go quickly through configurations that we have now for our production experiments and planning. So as I said, we'll include the more simplified chemistry T4S. We will have an aerosol scheme that's called MEM5. So there's a fifth aerosol mode that is for the stratosphere for interactive chemistry. We do have the new dust scheme from Danny's paperwork, and online emissions with our machine learning approach OASIS, and we add additional emissions to DMS as well. And then there's a lot of development still going on, and potentially we're hoping to put that in some production experiments and maybe some tier 2 experiments, like adding photolysis, interactive photolysis to UV, and Doug and June are really heavily working on this right now. Then the work you will hear about on the short-lived halogens for Rafa, Carlos, and others working on that. And then hoping to also have our updated soil NOx and others here, marinogenic emissions, Megan-3 biogenic emissions, also focusing more on improving the MEM 4 or 5 and karma chemistry, aerosol work, and we will continue including the HEMCO emissions and also including them in comp sets in the future. And so what we have done so far for the development, we tested various simulations more like for present day, 1980 to 2015. And so far, the model is looking quite reasonable. We did find in the process some problems and bugs that are fixed. Like, for instance, we had some problems in our biogenic emissions in the T4S mechanism that we could fix. And so we'll continue waiting for updates from the dynamics, from the WCAM group, or from the dynamics group to continue testing our chemistry. And so one thing we also do is look at the Chem6 physics because we want to provide also some configurations with the old physics scheme that people still can run, like finite volume grids and lower vertical resolution grids. And so Sean is also talking about it in his talk at the end of this session. That's developments in progress. Well, a lot of work in recent months also went in getting the new CMIP7 forcings that we have to use for potential CMIP7 simulations, of course. And so I will go through those in a little bit. You know, all those forcing need to be tested. And last time with CESM 2, when we included the new emissions, the model suddenly showed a very different climate. To know what is coming, what we're doing is we run a WCAM 2-degree model version that is our old, basically, configuration, but then with the CMIP6 emissions and then with the CMIP7 emissions to see what is going to happen. And Doug is leading that simulation, which is in progress. So for the forcings, we do have the volcanic forcing as a 2 emission database now available. So all the volcanoes in the past, from even from 1750, are listed here, and differences between the old data set and the new data set are basically indicated by the red points. That was the old data set that is different from the new one. So the new data set is an update done by Thomas Aubrey and others. We have a bit more different injection heights based on new observations in part, including inclusion of missing eruptions from previous data sets, satellite era improvements, especially in the last, from 1970 on, and then new smaller volcanoes, in the time before the satellite era, so we have more a balanced forcing throughout the year. And another thing we need to develop is a pre-industrial volcanic forcing SC2 emission data set to run pre-industrial with some elevated emissions. That's something what CMIT has done in the past. And those elevated emissions usually will also be used for future model runs. So we developed that with Ilaria Praya especially. And so our new data set here tested in an we have tested it in an 1850 model run, but comparing to present day observation just to see what about the forcing would be. So this is the new forcing is in from CMIP7 is in blue, and the old is in orange. So there will not be much difference. We also ran the new data set in our T1 T4S mid-top model, and basically the old CMIP6 data set is shown in pink, and the new CMIP7 in yellow gold, so there isn't that much difference over the Mount Pinatubo period, and as well as for later times, 1995 to 2015, for small volcanoes, it's fairly similar to what we had before. Then also Luisa, Rebecca, and Ben worked a lot on anthropogenic biomass burning forcings, and so here are two examples. What will be different? Very interestingly, carbon monoxide, for example, will be different, especially important for air quality and ozone. The old CMIP6 data were a bit higher than what we're going to see now in the new data sets. Differences are also shown in aerosols, like here primary organic matter. We do see some changes in the emissions, which will be very interesting to see what the impact will be on ozone and forcings. And then Jun also worked on the lower boundary conditions. CMIP is providing 43 greenhouse gas concentrations for CMIP7, and most of them are very similar, but one that really stands out that we're showing here is the carbonyl sulfides, because in the past we have seen, compared to observations, that we have quite a bit of an overestimation of those lower boundary conditions, so we're going to fix that as well. What we also were working on was our diagnostics. There is the ADF diagnostics, and Rebecca and Sean and others has worked hard in the last month and year to really put in some chemistry diagnostics. We now have running operationally, so you can download, get up this ADF diagnostic, and you do get these diagnostics already included, like ozone climatology, chemistry aerosol comparisons, budgets, AOD comparisons, CEOMOPID work, and we're still also working on WCAM diagnostics that look really nicely at the dynamics. And another data set, another comparison tool that has been developed, especially in the last year, is the Melodies-Monet framework that is very nice to do evaluation, especially of aircraft campaigns or observations like ozone zones shown here, and that really matches nicely results of specific observations, timing, and location. And Luisa will talk about that more in her talk. And then one thing, oh, now my daughter is calling. Sorry for that. So the other thing I wanted to point out is that we are actually participating in a lot of assessments and intercomparisons. And, you know, chemistry and this working group, including WCAM and ChemChem, is very active in those activities. I want to show a little bit what we have done, what we are doing right now, and what we're going to do. And we also want to learn from all of you what you're interested in to do and participate in. So we have done, of course, the CMIP6 simulations. And one thing I forgot here actually is the N2O assessment that some of us worked on in last year's work. And then we're participating in CCMI simulations. There's the big Hunga-Tonga assessment, and currently they have a working meeting at the MESA lab, so we don't have many contribution from people here today. We do GeoMap work, ISOMAP, which is an interactive stratospheric aerosol model intercomparison project. We do have, we want to participate in HTAP simulations. I have a couple slides on this here. And then also Rafa and others working on VSL MIP. If you have questions, ask them. And for future plans, so we hope for our CMIP ready simulations to be done, obviously the deck and other future scenarios with, as I already said, I have a mistake, the T4S chemistry. Sorry, see, it's still in there, the wrong things. But then also GeoMIP fast track simulation, and definitely interested in AirChem MIP simulations, especially with our more improved model version that we're hoping to have the VSL model version, and hopefully also with interactive methane. And so for the HTAP, Luisa and Rebecca are really leading this, and I'm not going to go through this in detail right now. But you can read it. It's really for looking at remote and long-range transport, for effects on regional sources, for effects on wildfires, methane, and so on. So there are two parts. One is more the anthropogenic, I guess, experiments, and then the fires as well that Rebecca is leading. And so I do wanted to show just quickly 3 slides from other science highlights because those weren't shown before Dave yesterday. But since we have almost no time, really go quickly. Just quickly a slide from Ilaria Kraya on Hunga Tonga. She's looking at radiative forcing of the volcano. And secondly, Beruth is here. He is working on future oceanic emissions that are updated in the model, which are important for the ozone development in the stratosphere. And finally, we're still working a lot, actually, on our impasse grid with chemistry. Ren and Mary Bartz are leading those efforts, and we're looking into more details on that. But with this, I need to stop. We are at the 15 minutes, so thank you for your attention. And I think we will, if you have any quick questions, urgent, let me know while we transition into our online presenter. And else, we will have a discussion before the break. And so then we can go into those questions in more detail. Okay. So I think we have our next presenter online. Do you want to introduce? Or I don't have it.
Yep,
yeah?
I've got it right here.
Great.
So our next presenter is Samantha Lee, who's joining us from Australia, where it is very late. So thank you for staying up to talk with us. Sam is going to talk about evaluating some initial evaluations of model and observations for a field campaign in Australia. Take it away, Sam.
Good morning, everyone, and thank you so much for having me today. I'd like to share with you some of those initial observations on some work I'm doing relative to Australian extreme bushfire events and comparing those to some models. But just to jump back a little bit and give everyone some context, in 2019 to 2020 summer season, the southeast of Australia faced one of the worst bushfire seasons in its recorded history. And in this graph here that I have, the estimates for the forest area burnt in that summer period was more than double any previous year. And this image from the NASA Worldview that I have, it was taken on December 31st of 2019. And it shows just the extent of the fires that were happening in this period in this region. Coincidentally, the characterizing organics and aerosol loading over Australia, or I will be referring to as the Koala 2020 campaign from now on, was placed in this region that I've indicated here, and it was measuring atmospheric chemistry emissions over this period. It's currently the most comprehensive smoke data set that we have for this particular region. This represents a huge opportunity for us to use this data and compare it to model outputs and see how well these models do at producing the emissions and the concentrations of the atmosphere during this very extreme smoke event. This would obviously help with future climate research and emission studies, as well as assist in air quality management and the dissemination of public health advice from stakeholders of this project. So overall, what I want to do is I want to take the koala data that we had measured in situ, and I want to compare that to ultimately 3 atmospheric climate chemistry models. And I want to see how well they represent the chemical species in the concentrations of smoke plumes during this one extreme event. And I will hopefully be able to present a range of these and their specific effectiveness within the Australian context. So this is the one of the best images I was able to get from the actual koala site. And on the back of this large truck, there was this airbox, which was deployed and had multiple instruments present in it. And each of these instruments was running at some point during the December 2019 to March 2020 period. There's a large mast on top of the box, and that's about 20 meters high. So this koala data set is really a point-based data set, and it's only the surface layer of the atmosphere. So this research is only taking into account just that one layer. Just to quickly show you the diversity of the instruments that we had available at the koala site, this is just some of the chemical species that were measured over this time period. So we have a lot of data here that we are able to compare with models. But in order to do comparison, we need there to be data that is present, not only measured in koala, but also modeled in the atmospheric chemistry models. So from that, I pulled out the specific ones that are relevant to stakeholders within Australia, as well as that ones that are particularly relevant either because they have a human health impact, as well as contributing to atmospheric reactions, or are just straight up greenhouse gases. And I will give a little bit more context on ozone and PM 2.5 as I go through this presentation. I plan on comparing 3 models in this work to the point-based data, but at this time I have information for 2 of those models. And the one that I do not have information on at the moment is the WRF CMAC model, which I'm currently in the process of running with the New South Wales DQ, one of our government departments. But I'll give you some context on the AQFX. This is a regional atmospheric model, and it was developed by the CSIRO in Australia, one of our national science agencies. And thanks to Julie Noonan over at CSIRO, I was able to obtain model data from this model over the course of the 2019 to 2020 summer bushfire season here. The model was able to give a 9 kilometre by 9 kilometre resolution with averaged hourly concentrations. It's only been developed to model Australia, specifically the southeast coast of Australia. So it's a highly regional model, and it was actually developed to model smoke plumes, particularly for planned burns in the region, so that the government could then get an idea of where the plumes would head and what sort of warnings they would need to give to people nearby. I've also put here the inventories used, which they use the State Environmental Protection Agency inventories, and they've developed specific data for the fuel layer map from the AFDRS, and they've also determined experimentally their own emission factors and have used this in this particular model. The weather modeling for this was also obtained from the Bureau of Meteorology Access. I've included here an infographic from this paper, and this is the overall structure of the AQFX model. And feel free to have a look at this maybe a little bit later, ask me some questions about it, but this is the overall architecture of the model for measuring those smoke emissions. The other model that I had access to, thanks to Rebecca Bucholz at your own organisation there, is the Musica model. So this is a model that was able to be obtained for 100 by 100 kilometre resolutions. And it is a global model, and people here probably have more knowledge of this model, so I won't linger here for too long. But this is another one that I'll be using for the comparisons. So to go on, I've prepared some results here just to give a preliminary understanding of what the data is looking like, and starting with ozone for those comparisons. Here we can see that the spread of ozone across that summer period was quite similar between the koala measurements and the 2 models. There was a slightly larger spread for the Musica model in this instance. I've plotted the concentration of ozone across the time series here, with the point measurements being in orange and the 2 models being present in the blue and the green. And here it was interesting to me that we could see that while there was a difference in the concentration readouts, there was really good covariance between the models and the measurements. And so this had us go to our stakeholders, and we had an interesting conversation about sometimes they don't really mind so much as to what the actual concentration is, but they want to know whether a regulatory limit has been exceeded. So I'll be speaking specifically about the Australian regulatory limits, but they start to issue health warnings when the ozone concentration exceeds 115 micrograms per meters squared. So we can turn this question into one of a categorical question. Instead of asking what the concentration was, we can ask the question of, was an exceedance event predicted? And then we get to make one of my favoritely named things in science I've come across so far, the confusion matrix. So we determine when the model got it correct in that there was an exceedance event, when it was incorrect as to when there was not a exceedance event, and take that and make a confusion matrix. And here I've just represented AQ effects on screen left and Musica on screen right. With the green squares indicating that this is when the model was made a correct prediction, and the red is when the model made an incorrect prediction. So here it's worth noting that this is a highly unbalanced data set as well. There were more true negatives than any other category. So this will skew some of the metrics that we'll talk about just a second. There are a lot of different metrics that we can look at for this particular kind of exceedance event evaluation of a model. These are just a few of the ones I've looked at so far, which is the accuracy, how often a model is correct, how often a positive prediction is correct, which is the precision, the recall, which is how many of the positive events that it was managing to capture, and the F1 score, which is an average of the precision and the recall. When we do all that math and we plot it up on this table, it looks like the accuracy is quite high. Both of the models get to about 90%, but this is, as I mentioned earlier, because of the highly unbalanced data set. Both of the models perform quite similarly in the case of ozone, the F1 score for both of them being 0.64 and 0.6, which is not ultimately too different between the two for ozone. And I'll just quickly run through the results for the PM 2.5 as well. I've done the exact same analysis with PM 2.5 and presented those results here. With the box plots, the AQFX model in this instance had a much lower spread of data, and it was often underreporting the PM 2.5. And Musica came much closer to representing the actual concentrations of PM 2.5 in the atmosphere. Plotting them all again like this, and again using the New South Wales regulatory exceedance level of 16.75, we can do the same thing again. We can make a confusion matrix, determine when the model was correct and incorrect. And in this instance, the PM 2.5 data is a little bit more spread in between. And here we can see that there is actually no false positives events in the AQFX model. And that was mostly because the AQFX model underrepresented the PM 2.5 concentrations. So it rarely had a false positive, but it was more because all of the values were a bit lower than they should have been. Plotting all that up, in this case, the F1 score is quite different between the two. The AQFX had F1 score of 0.42, while Musica retained 0.73. And so in this instance, the ozone might have been better represented in the AQFX. However, Musica seems to have better represented the PM 2.5. So this is some interesting data. Both of the models covaried well with the actual environment, with AQFX representing ozone slightly better and Musica representing the PM 2.5 concentrations in this extreme bushfire event. I also just wanted to end with saying I do plan on doing an in-person visit to NSF NCAR on the 4th to the 15th of August of this year. So if you find this interesting and you'd like to talk to me about it in person and you happen to be around, I'd be more than happy to talk to you. Or if you have any other data that might be of interest to this study, happy to chat about that. Thank you very much for your time.
Thanks, Sam. We have time for one quick question, if there are any.
Thanks for the talk. I have a quick question. So where was the location of the sampling in the model, and where was the truck located? It was a urban state. I mean, it was located close to a urban, into the forest, or did you evaluate the model outside of that pixels to see if the ozone evolution was different in other locations?
The Koala 2020 campaign was originally planned to measure the biogenic emissions. So it was placed about 60 kilometres south of Sydney, about 30 kilometres inland from the ocean, in just a pristine eucalypt forest. And the modelling for the AQ effects, we did a 9 kilometre by 9 kilometre grid, and I specifically looked at the grid square that was over the location of the koala campaign. And similarly, the Musica was centered across in that location, which I had in this slide right at the beginning. Yeah, here. So this is the location of the koala measurements, and both of the grid squares that I'm looking at were specifically laid over this. And it was chosen because it was relatively far away from anthropogenic sources of emissions and set in a eucalypt forest.
Next speaker, thank you again, Sam. And we're continuing the conversation about wildfire, looking at aerosols now and their relationship to temperature, and Sean Lester will be coming up to talk.
Oh, wow. Okay. Oh, thank you. Appreciate that. Sean Leister, and oh, yes. Hello, everyone. My name is Sean Leister, and here I'm here to talk about some new experiments that we've created and looked at to understand simulated fire aerosol climate interactions, and how these ultimately drive hemispherically asymmetric climate responses and reduce global climate variability. So here I just want to start with an example, starting on the small scale and moving on to the larger scale. On the left, I'm showing a global satellite image from the NOAA Discover satellite on May 31st, just a couple weeks ago. And circled in red, I'm showing Canadian wildfire smoke over large regions of North America and over the Atlantic Ocean. A few days after this image was taken, news articles were published highlighting how this smoke has been advected from Canada across these regions, nearly globally. And so we can look at the forecast of this Canadian wildfire event. And over the 10 days, we can see how first the smoke is advected eastward and then is distributed by the circulation north to south across North America. And then it's further advected eastward towards Europe. So this diagram begs the question of, since we can see these smoke from space, and we know that it's globally distributed, how does the smoke affect climate? And this question has largely gone unanswered, but a few studies have actually worked to try to understand this and answer this question. So by isolating variability in climate models, specifically here CESM2, this study found that variability in fire emissions has causes simulated sea ice to decrease faster than without. Consistent with this, another study found that variability in fire emissions drives warming across the northern hemisphere extratropics. But even though we've gained understanding from these studies, the climate impacts due to fire emissions remains uncertain, mainly because emissions are prescribed in global climate models, including CESM2. So here I'm showing the prescribed fire emissions from 1950 to 2070 across 40 to 70 degrees north, and it's shown in black. Notably, from 1997 to 2014, the fire emissions are prescribed using observations rather than historical climatology that is smoothly varying. So we see this sharp discontinuity in variability from before 1997 to after, and then from before 2014 to after, from here to here. So the results that I've just showed you on the previous slide are based on this discontinuous variability and are only over this present day period, because that's when we can understand the difference. Furthermore, and probably more important, is that the fire emissions that are prescribed in these global climate models do not match the climate state that they occur in, meaning that the prescribed emissions are prescribed regardless of the surface temperature anomaly. So it could be anomalously warm over a certain region, or anomalously cold, or it could be anomalously wet or anomalously dry. The prescribed emissions are the same year to year. And just to illustrate this point, here I'm showing the cumulative area burned in Canada with observations from 2012 to 2023, or seasonally. And we can see that the annual variations in total area burned are large, ranging anywhere from 1 million hectares to up to 16 million hectares. So the prescribed emissions do not capture this. In addition, the prescribed emissions do not capture the seasonal variability from year to year. So we cannot answer some really fundamental questions of climate-fire interactions with present-day capability in climate models, such as like how would a realistic evolution of fire emissions affect the climate? What is the long-term climate response to fires? Do fire climate feedback significantly change over time? And how important are fire emissions to regional and global climate change? So here we use the Community Earth System Model 2, or CESM2, with new interactive fire experiments to resolve this issue. And this new interactive fire experiment has 5 members, and it is taking direct prognostic calculations from CLM5, which is the land model or land component, and putting them through the coupler to the atmosphere model, or CAM6. And in order to isolate this fire response due to interactive emissions, we also compare the new interactive experiment with the prescribed experiment, the CSM2 large ensemble. And CSM2 is a very good model to use because the large ensemble has 50 members, which gives us insights into variability, and it also simulates cloud aerosol interactions, which is important to understand the fire response. And so with this, we can understand, or we can try to answer our main research questions, and which are fundamental to understanding the climate system as a whole, which are what are the impacts of interactive fire on the mean state, variability, and trends under climate change. So first, starting with the mean state. Here, I analyze the mean state by looking at mean climate responses over the individual experiment pre-industrial controls to understand the change without additional forcing. And to begin, I'm looking at primary organic matter, or POM, or primary organic matter, or POM, and specifically its burden, or its mass in the atmosphere. And I'm first in the top panel, I'm showing the POM burden in the interactive experiment. And in the bottom panel, I'm showing the POM burden in the interactive minus the prescribed to understand the change due to prescribed, the change in the spatial distribution. And we can see that in the top panel, generally we see that POM burden is distributed globally, and it's concentrated over land masses, which is expected. But somewhat unexpectedly, we see that the change in palm burden, or the spatial distribution change in palm burden, is hemispherically asymmetric, with more palm burden being in the interactive experiment in the southern hemisphere, up to like 10 to the negative 7 to 10 to the negative 5 more palm burden in the southern hemisphere, and less palm burden in the northern hemisphere, from around 10 to the negative 6 to 10 to the negative 5 kilograms per meter squared. And we see that these interactive emissions drive hemispherically asymmetric mean climate responses due to these aerosol radiative effects downstream from the palm burden differences. First, we look at the shortwave cloud radiative effect, or SWCRE, and we see that the difference, there's generally lower shortwave cloud radiative effect in the southern hemisphere and generally higher in the northern hemisphere, suggesting that clouds may be becoming more reflective over the southern hemisphere and less reflective in the northern hemisphere in the mean state. Spatially coinciding with these differences are temperature differences, since they directly depend on radiation. And we see, again, that across the southern hemisphere and the Atlantic Ocean, lower surface temperature with interactive emissions regionally by up to 1 degree less than prescribed. And near the Arctic and northern land masses, we see a rise in surface temperatures. And consistent with these results as well is a change in the distribution of precipitation, specifically a northern shift in the ITCZ. Next, we look at the variability differences caused by interactive emissions. And so again, we look at the pollen burden variability, and we look at this over the period of 1850 to 1990, since this is a period without rapid change. And we can utilize the power of ensembles to look at it. First, we see that, as expected, pollen burden variability, interannual variability, increases nearly everywhere with interactive emissions, just because they are interactive. But surprisingly, those interactive, that drives a decrease in interannual variability of many different climate fields, including the shortwave cloud radiative effects, temperature, and precipitation. And these are near global lowering of climate variability in all of these fields. Lastly, we examine the interactive emissions impact on climate trends and feedbacks. And so here I'm showing a time series of annual global mean pollen burden in each experiment respective of its pre-industrial control. And I'm showing that and I also just want to note that the similarities in the global mean are somewhat due to prescribed land use and land cover in CSM2. But notably, there are differences in the historical period and late 21st century. So that's why I'm highlighting these. And I want to understand the evolution between these two periods, over these two periods. So to understand the evolution, I plotted I'm looking at the change between the pre-industrial to 1990 versus the change from 2021 to 2100 in these different climate fields. And we can see clearly that over the historical period, there's not much change in the radiation or the shortwave cloud radiative effect or temperature. But we do see a significant northward shift of the ITZZ. But the largest evolution or growth in these fields is from 2021 to 2100, where there are large radiative effects, especially over the equator. And in surface temperature, there are a lowering of surface temperatures across the globe, especially in the northern hemisphere extratropical regions in Northeast or North America, by about more than 2 degrees Kelvin, due to interactive emissions as fires spread across the globe. Okay, so in conclusion, this study shows, I want to highlight that this study shows that these interactive emissions induce substantial hemispherically asymmetric climate responses driven by these fire aerosol climate interactions. Also, the interactive fire emissions cause persistent global decreases or reductions in interannual climate variability near globally, especially for surface temperature. And finally, the fire aerosol climate interactions reduce the trend in global mean surface temperature by about 0.8 degrees regionally throughout the 21st century, or globally throughout the 21st century. And regional reductions in surface trends can decrease by more than 2 degrees with interactive emissions.
Very much, very nice talk. I think what is really interesting is the north-south difference that comes up. And you know, interactive fire emissions seem to be something we want to have desirable in the model since it is much more interactive with the system. However, the observed fire, the prescribed emissions are somewhat observed, right? So you wonder, can we actually rely on the interactive fire emissions to give us the right signal, like this difference? So what do you think, what is causing this difference? Is it because maybe our land, our rainfall, all those things may be not quite aligned with observations, or is it that the observations may lack information that we should trust more our interactive fire emissions?
Yeah, I think that the interactive fire is quite important, and because specifically that we can't rely on the prescribed fire because of these discontinuities in variability and mean responses. But the interesting thing is there are model biases in the area burned, which can cause these across the southern hemisphere and the northern hemisphere, which can cause these differences hemispherically. But yes, I do think that the differences are mainly due to the climate responses, being that the climate states do not match in the interactive from what I've seen so far, or in the prescribed from what I've seen so far. Thank you. Okay, thank you.
Thank you. We also have discussion at the end where we can continue as well. Our next speaker is Louisa Emmons, who will be talking about Asia AQ and analysing those observations.
Right, thank you. Yeah, okay, I think right. I just wanted to, so a lot of people are involved with the Asia AQ experiment and analyzing it, and we have 2 visitors this summer I just wanted to mention. Hayrim Kim from University of Iowa and Yifan Chang from University of Illinois are helping out with various aspects of model evaluation and analyzing the observations. So we haven't yet had sort of an overview of Musica, just in case anybody's not familiar. Our nomenclature, we're really just calling a configuration of CAM-CAM with regional refinement, Musica, version 0 and version 1 now. So we've had version 0 for quite some time with the spectral element dynamical core that you can make a refined grid in. And Musica V1 we are currently evaluating, which uses the MPAS dynamical core and has the hexagonal grid. If anyone would like to start using Musica and is not yet, we have a lot of materials online. We have a wiki page. We've held a number of tutorials, and all that material is available from the wiki page. There are currently several grids that are available within CESM, the Arctic grid and a CONUS grid, as well as the Greenland ice sheet, a subset of this. And you can make your own grid, such as this Nori Mariscal, who just received her PhD at Wayne State, made a grid of 7 kilometers over Michigan and 100 degrees for the rest of the globe, so you can look at a very small region with refined grid, and you can even make multiple grids within one. As I said, Musica V1 is being tested. So AsiaAQ took place a little over a year ago in February and March, and was a rather complex campaign led by NASA with two NASA aircraft, a lot of ground measurements, a lot of modelers. Started out for the first half of February in Manila, then went to Seoul from mid-February to mid-March, and then looked at Thailand the second half of March. And so it was really focused on looking at urban regions, so Manila. You can see that these regions are all quite different. Manila, down in the tropics, is quite isolated and relatively clean around it. This is a picture of NO2 from GEMS. Seoul has a huge megacity, and it greatly influenced by China. The Thailand region, we sampled Bangkok, but we also flew up to the north and sampled the fires in northern Thailand and Myanmar that influenced air quality. So there were a large number of measurements. The 2 aircraft worked in tandem. The white line shows the DC-8 flights, which sampled between the surface and 4 kilometers, did a lot of profiling with a huge suite of in situ measurements, a lot of detailed chemistry, aerosols, size distributions and composition. And then a high-flying aircraft sampled out the urban region with a with a remote sensor similar to the GEMS instrument to measure NO2 columns and formaldehyde columns, as well as having a LiDAR, the HSRL, which measured ozone and aerosol profiles over these urban regions. So it's a very nice complement of detailed chemistry and detailed sampling over the urban regions. So for my work, I've been looking at Musica for this period, and I created a grid with fine resolution over each of the continents in the Northern Hemisphere, and I have a couple different versions of the grid just over Asia. So to be a bit cheaper, there's a grid with 14 kilometers over only Asia, also a 25-kilometer grid for even cheaper simulations. And we also grouped it at NCAR ran WRF with tracers and are now using WRF Chem for the analysis. And so we're using all of these different observations to try to evaluate them. But we're currently focused on developing an emissions inventory that can be used by all the different modeling groups that were part of this campaign. There were a number of NASA-funded groups as well as the groups in each country. And this is just an example of the different inventories that are available around Bangkok. There's a local inventory, which we think is probably most accurate. And some of the other inventories that we've used, the mix inventory is a combination of a composite of different inventories in Asia. CEDS, which is the basis for the CMIP emission inventory, and EDGAR. So they're all very different for Bangkok, and similarly, several different emission inventories are very different for different regions. So group in Korea is putting together a composite of all these different inventories. The fire emissions, of course, are also very different. We have FIN on the left here and QFED in the middle for one day, and so we're still evaluating whether their which is most accurate, and also looking at the VOC speciation, which we have all the detailed VOC data from the aircraft to help evaluate that. And VOCs and the anthropogenic inventories are also very different. Asia AQV3 is the first composite we used for the campaign. Propane is very different, toluene is different. So having the different ratios of these reactive hydrocarbons can make a big difference in ozone production. So now to what some other people are doing. Jun Zhang is putting together simulations using the tagging of NOx to look at the source attribution for ozone. And so we tag NO through to NO2 and all the NOI species, and then the amount of ozone that comes from a different NOx source. So this is just some of our preliminary results showing the tagged ozone. This is the total ozone, simulated ozone, and then versus anthropogenic or fire from ozone for these two sites in the Philippines, Manila, and a more remote site. So clearly up north where there was some fire influence, they're comparable, but in the city, they're anthropogenic is more important. And Hayram is doing some similar work, source attribution, a completely different method in WRF Chem, and that is, or WRF CMAC. So we'll compare with that. And Yifan Cheng, visiting from Illinois, is working on updating the representation of urban properties in the land model and looking at how that impacts ozone air quality. And so she's just started, but she's already made great progress, and I'd have results if the computers hadn't been down for the past week. But so we can, this is really valuable for Asia AQ, which was really focused on understanding the air quality in these urban regions. So there's a USERP data set that was, that she's implementing, and it changes the properties, the thermal, morphological, and radiative properties for things like the roofs, canyon floors, and walls of the buildings within the urban regions. So she has done a little bit of a run already with, she's using the grid I made with the 3 fine resolution regions over North America, Europe, and Asia. And you can't really see that, but so this is the control and the surface level. So in general, the ozone amounts are the same, but if you look at a difference plot, you can see in urban regions, we see quite some large differences, some plus or minus at least half a BPB in some of these urban regions. And next, Wenfu is testing out Musica V1. She has just started getting some good results. And so this is, she set up the MPAS grid. Beirut and others have been helping as well. Set up a 3-kilometer grid that covers the Philippines and Taiwan for our regions, with 60 kilometers for the rest of the globe. And so this will also be a really great test of this high resolution, and I think will really help us understand these observations. So sorry, for a lot of this work, we'd really like to use melodies, which we've been developing over the past few years. And any day now, version 1 will be released, and it allows for, as Simone mentioned before, allows for detailed comparisons of observations to models, so matching the exact time and location. The atmospheric diagnostic framework that we've been also using is more for climatological comparison for long model runs and with climatologies of observations, but for analyzing specific aircraft campaigns and using surface observations like the EPA Air Now data, Melodies Monet is set up to do this exact comparison. And so we have a number of data sets all set to read in it, aircraft campaigns that are in ICART format, a variety of different satellite products, and Some development versions have Pandora, and we're also working on reading in the GEMS data. So the framework has readers for each of these different observations, puts them into a standard format, can read a variety of models. I didn't list that, but CESM FP, CESM with the spectral element, WorfChem, variety of other models. And then you set up what you want, what sort of comparisons you want to do in a YAML file, and you don't have to write any code. And then the driver pairs the model with the observations, and then you end up with paired data, and plots and statistics are generated. So it makes plots like these. The model overlaid with the AirNow observations, and then box plots, violin plots, whatever you want. For Asia AQ, this is just an example of WorfChem and some Asia AQ observations. So you can have time series, you can have a curtain plot of the model as well as the observations as a function of altitude and time, and vertical profiles comparing the observations and models as a function of altitude for each species over whatever region you want. And it's just an example. We also can compare with Moppet and see, get difference plots over the whole map. So there's going to be a large Asia AQ model intercomparison once we decide on get a finalized model emissions inventory, and so we'll be participating in that. And I just want to say that we welcome users for Melodies, Monet, and Musica, and welcome your contributions and testing of them. Thanks.
It says for Louisa. What's that?
Go ahead.
From Musica, what is the driving reason for us to switch the dynamical cores?
Will allow us to go down to the finer resolution of 3 kilometers. So the Musica V1 spectral element, we really can't run below about 7 kilometers. Did I say that right? So with the MPAS core, we'll be able to go down to 1 kilometer. We currently have grids that are centered at 3 kilometers.
Okay, let's move on to our next speaker before the discussion. Saida Mohammadi will be talking about volatile methyl siloxane and the oxidation, aerosol formation, and aging.
Sorry. The first slide. I wanted to see how to use pointer. Okay.
Yeah, so
This one?
Yes.
Okay.
And just point right.
All right. Thank you. Hello, everyone. I'm Saide, PhD student from University of Iowa, and I'm going to present our work of modeling volatile methyl siloxane, or VMS, oxidation, SOA formation, and aging using CSM2 and Musica version 0 framework. Outline of presentation, I'm going to start with a little background of VMS compound and the motivation, moving to model setup, simulations, and then I will dive into the result and model evaluation, and then end it with key takeaways and representing feature works. What we know about volatile methyl siloxane is that they are a synthetic compound, high volume, human-made, and they're characterized with silicon oxygen, the alternating silicon oxygen bond with 2-methyl group attached to silicon. They are found in mostly in personal care product and also industrial lubricant, glues, and cleaning detergent. Some of the important cyclic volatile methyl siloxanes are D4, D5, D6, with the number representing the number of silicon in their structure. And D5 is one of the predominant and ubiquitous CVMS in the atmosphere. So about the fate of VMS in the atmosphere is that whenever you apply your personal care product, they are highly volatile. More than 90% can evaporate, go to the atmosphere, and finally they can react with hydroxyl radicals and with a few to several days of lifetime in the atmosphere. Comparing the global D5 to other anthropogenic emissions like benzene is not too much, but this is not the whole story about the D5 in the atmosphere. They have a potential of long-range transport. They also are classified as very persistent, very bioaccumulative under Stockholm Convention on persistent organic pollutants list at 2023. And all the evidence of aerosol formation of this compound are listed here. All these studies are either chamber experiment or oxidation flow reactor, so experimental work, or few of them are field campaign. The most recent one, which is published from our collaborator when we did field campaign in New York City during 2022 summertime, is Mipich et al. It was a combination of lab work and also field campaign. When we observed, and this figure represents that the oxidation product of D5 that were present in a particulate matter sample collected from New York, you can see the first generation oxidation product with one hydroxyl group substituted to methyl group, and also the second generation in New York City samples. So the one important key takeaways from all these studies and also the New York City field campaign in our work is that the oxidation chemistry of D5 is actually multi-generational. Why do we need to model CVMS? Because of the widespread use and the emission, and also the potential of long-range transport, and the bioaccumulation and being persistent in the atmosphere. And we also have the available gas and particle concentration due to the NYC Mets field campaign during 2022. So we can evaluate the model. And also the parent and daughter compounds proposed as a tracer of personal care product. But a specific daughter molecules, their lifetime, their first partitioning are also needed. Here is what how we modified the musical model. So for the emission of VMS compound, we use the Brunei et al. 2025, which is the other collaborator of this research. We just submitted the manuscript last week. And for this, I started the simulation with CamCam because of the computational cost. We wanted to see the reasonable result for SOA with 1 degree resolution. And then we moved on to regraded in musical resolution with finer resolution. And we have 2 sets of reaction mechanism for CamCam simulation. We wanted to see actually the SOA formation of D5 at the first step. And also we wanted to study the aging effect of aerosol. We didn't consider silicon conservation in the reaction mechanism at the very first step of our simulation. And the musical simulation is with much more updated mechanism. And also we wanted to see the multi-generational and aging with silicon conservation method. Here is a schematic of the VMS emission from Brunei et al. 2024. So what they did is that they took sales data and also sales data for personal care product and population density, and they scaled the per capita emission globally. And this figure shows the gridded emission for Musica grid with 14 kilometer over CONUS and around 100 kilometer for the rest of the world. The big caveat in this emission file is that we only use the data from personal care product usage, not industry, not water treatment plant. The reason is that there are not any available data from industry or other sections. And also, Brunei et al. Did an evaluation of actually D5 emission with this method, and it was in very good agreement with measurements. Here is the zoom of D5 emission over CONUS. You can see the pattern of the hotspot in the CONUS is mostly over the urban areas with high population density. For example, New York City with one of the hottest spots over CONUS, comparing to Chicago. And I also included Denver, Colorado emission. You can see how it correlates with population map. So the SOA formation in CAM-CHEM is based on the volatility basis set scheme. So in the VBS, actually VBS tracks the VOC oxidation product by their volatility, and by distributing the product in 5 volatility bins that they can further partition to the aerosol phase. With the first bin being least volatile, the most probability to partition to the aerosol phase, and the last bin being the highly volatile oxidation product with less potential of aerosol formation. And this reaction mechanism shows the general mechanism, which how we define aerosol formation in the model. These coefficients alpha over for the SOAGs are actually experimentally these molar yields are defined based on the experimental work. As we see here for specifically D5, this figure is SOA yield versus OH exposure, and the second axis represents the equivalent photochemical age, days. And all these data are available SOA yield for D5 from different studies. And these dashed yellow line represent the 5 days, which is about a 1 lifetime of D5. And here, the highlighted area represent the more atmospherically relevant environmental condition, experimental condition. So this is basically the same data, but the other way of showing that the SOA yield versus D5 reacted. What we did was we fit this line for all these data, and best molar yields chosen via non-negative linear least squares. Here is how we define the D5 aerosol formation. As you can see, most of the molar yields are only distributed over 2 bins. The first bin, which mostly are less volatile and are in the aerosol phase, and the last bin, which most of the oxidation product are in the gas phase. And we also use the extended version of VBS. In the extended version of VBS, each of the SOA are assigned to their source. So in the CSM default, there is SOAs from fossil fuel, presented as SOAG-FF, biomass burning BB, and biogenic BG. And what we did when we wanted to add the D5 SOA, we put all the SOAs from fossil fuel and biomass burning and assigned the SOA GFF for all of those sources. And we assigned the SOA from D5 to SOA GBB and kept the biogenics as SOA BG. Here is how we define the reaction mechanism. We represented the gas phase oxidation product of D5, the first step, and OD5 actually is the bulk oxidation product, and which can also, D5 can also form the aerosol in this reaction mechanism. For the simulation, when we wanted to see the effect of aging, for the case that we have D5 SOA and aging, we represented the aging for considering functionalization only, where each of these volatility bins can move one bin lower, knowing as functionalization aging, and represented in the second case of simulations. Here is the global distribution of D5 species. As you can see here, the hotspot and highest concentration of D5 are mostly distributed over urban areas like Europe, China, east and west of United States. But however, the oxidation products are almost everywhere distributed in northern hemisphere. As you can see also in Arctic, you can see some concentration showing the long-range transport. This figure shows actually the SOA from D5. As you can see, the pattern of hotspot matches with D5 concentration, confirming that most of the SOA from D5 actually are highest wherever we have high concentration of D5. Here is the detailed volatility basis set, each bin's diurnal profile of D5 species for semi-volatile oxidation product and actually aerosol phase. I wanted to see the aging effect by including two cases. In all figures, orange solid line represents the D5 SOA, and the blue one is D5 SOA with considering aging. So to take a closer look, you can see in the bins that we had the 0 molar yield for the oxidation, for the SOA formation. We have the 0 concentration in this bin when we don't have aging. But when we included aging case, we can see the formation of aerosol. So in these two figures are a total semi-volatile and aerosol. You can see how aging can increase the aerosols from D5. And this figures actually shows the same thing, but with a special distribution for no aging case and aging case, and these two figures shows how aging affect the aerosol formation. And this figure actually is for the particle phase. We can see in the aging, there is increase in aerosols when we represent the functionalization, but the less gas phase semi-volatile oxidation product. So we evaluated the D5 derived SOA for both model, aging and no aging. So with aging, we can see the higher aerosol comparing the no aging. And we evaluating with the measurement with NYC METS sampling during July 2022 in New York City, which for 4 samples, the value was 6.6 nanogram per cubic meter. So both model actually underestimate SOA, D5 SOA by factor of 3 for aging. So aging is doing a better job of capturing the D5 SOA, but we have not yet apportioned the error to emission, SOA yield mechanism, resolution effect, or even it can be due to the analytical uncertainty that we are working on that. And we evaluated the other parameter in the model, PM2.5 and ozone. For the PM2.5, you can see the black and red line overlaid for aging and no aging cases, which shows that D5 aging shows minimal effect in other variables like ozone and PM2.5, but the ozone generally underestimate PM2.5 with good agreement with daily trend, and for the ozone, it overestimates. And overall, we saw the D5 peaks in urban area, and we saw the pattern of northern hemispheric and long-range transport. The aging effect actually enhanced the aerosol formation from D5 without any impact on any other variables. And it underestimates PM2.5, overestimates ozone. And as a future work, actually I submitted all these musical simulations, but due to the maintenance, they are still on queue. So looking forward, the next step is doing the higher resolution musical simulation with updated D5 chemistry. We wanted the result will be more consistent with experimental data, specifically with Kang et al., where they did experimental work to show the VBS from the D5. They showed that how the first generation oxidation product actually are very volatile. They don't form aerosol at the very first step of oxidation, and then they can further oxidize and form aerosol. So these are the simulations that I'm gonna do for musica cases to see multi-generational and aging effect. And I acknowledge my advisor, Dr. Stanier, and collaborator from University of Iowa, University of Colorado Boulder, and Dr. Joe from Seoul National University, and scientists here at NCAR. Thank you.
Maybe time for one quick question before our discussion.
Just a quick question. So what's the lifetime of the D5 VMS? I couldn't quite figure that out.
Based on the experimental work, there is a quite wide range of D5 lifetime in each of studies, but there is a range for that. If you consider chlorine radical oxidation, the lifetime is going to be much lower, starting from 4 days or 3 days, and spanning to around 8 days. So it's something between 4 days to 8 days. Yeah. Thank you. Yeah, thanks.
Okay, that was great. Thanks for all the speakers. We do have 10 minutes now or something like that before the coffee break. We do want to pick up on some questions that people raised earlier. Maybe we can just, we could go back to the first slide set on the introduction to have some start of a discussion. So are there any general questions to the model? We do have another discussion later on to the setup of the model to CESM3 experiments. And you can think about that. One thing I think I do want to come back was a little bit the question on the dynamical course, because we had very little time to answer that, maybe, because one question that I still have, and maybe when Fu is here as well, is on the dynamic course, really we can go to 7 kilometers with the spectral element in the regional refinement. For MPAS, I think, or my understanding is that currently in the global model, the cloud resolving parameterizations aren't quite included yet. Is that correct? Because we can develop these high resolution versions, but do we actually parameterize the clouds properly? Or are we actually, do we not parameterize the clouds, or do we parameterize them still in the model for the MPAS grids?
Right person to answer this question, but so for us using musica MPAS is just a dynamic core, so the physics is still from CAM. I think that's a question we need to ask the CAM team if they have developed or updated cloud schemes for that.
Yeah, I think that is actually part of the CIMA development, that we will have cloud resolving physics. I just want to, I think it doesn't have the physics changes yet.
Have to be made to for the non-hydrostatic dynamic core or for the convection resolving.
So maybe while you're here, you can also explain a little bit how easy it is to develop a grid for the MPAS model version, because, yeah, that maybe.
There's some details you need to figure out, and if you have experience with Musica version 0, it will not be hard to use Musica version 1. Although we are just started testing if it works. It runs for now, but we haven't really looked at the results to check if the results is reasonable. If after we check the results is reasonable, we will have a tutorial soon, hopefully in July. But as I said, you might need to have some Musica version 0 experience before you can move to Musica version 1, because there are it's doable, but there's so many details to figure out. Yes.
Maybe we can hand it around, or yeah.
That's the MPAS configuration is based on CAM. I mean, it uses CAM 6 or 7 or both, or for Musica version 1.
So we've tested Musica MPAS in CESM 3, so that's CAM 7, right? Yeah, you can specify either one.
For people, we have two versions. CSM3 basically is the new development version that we are developing going forward. And one thing is CAM7 will have new changes to vertical resolution and physics and other things. But there's also a CAM6 physics version available that we are testing, and those are slightly different, or actually in some major parts they will be different. And so there will be those two CAM7 and CAM6 versions available. Currently, probably the CAM6 physics version is the one we understand better, because the CAM7 version is still in development. That doesn't mean we can test it and look at it, obviously, and do that. Other question to dynamic cores or model setup? Yes? It should work.
So I'm really very ignorant here, but then from the CAM perspective, because I heard that the home dynamical core is being introduced to CAM, and then you will have the non-hydrostatic version down the road. So that's the cube sphere and so on. So from that perspective, it might make sense to stick to maybe still like pay attention to the SE die core and the cube sphere grid and so on, keeping that like a development in mind.
The core is the spectral element.
So because the CAM7 is already using spectral element, right?
Yes.
So I think they are using a hydrostatic version, if I'm understanding correctly. But Mark Taylor, Christiana Yanovsky, so they have the ongoing effort to introduce the non-hydrostatic version of SE. I think that's going on right now.
Good, because that will allow then probably the spectral element regional refinement to go higher resolution as well.
Right.
Okay.
I think Adam Harrington has been working a lot in that directions, and so he showed a diamond simulation, so like a convection permitting a resolution simulation. So keep that in mind. It would be useful.
And thank you. Yeah. Yeah, we need to keep track of everything. Yeah. Okay. I mean, other questions, I have brought up the different multimodal comparison projects that we have. I'm sorry, I'm going here the wrong direction, as well as the diagnostics. And I don't know what time it is now. We only have 1 minute. We can also just go to the coffee break and continue with this discussion after the break. So why don't we have a coffee break now, and then we'll talk about multimodal comparison projects and other questions at the end of the next part of the session. Okay, thank you. And all the speakers again in the morning session. And see you after the break. wait a minute since people are coming in. But I think I can introduce you already, because online people may be there already. So while people coming in, our first speaker is Rafael Fernandez, and he will talk about Arctic halogens reduce ozone in the northern mid-latitudes. And should we give you a notice after like 2 minutes before?
Yeah, sure. Yeah, you can just let me know. Well, thank you very much, everyone. I'm Rafael Fernandez from the National Research Council of Argentina, and I'm presenting these results I made with some of my students back in Argentina and in close cooperation with Carlos Cuevas and Alfonso Saiz Lopez from the CSIC in Madrid, Spain, where I've been working many years, and also with help with Doug and Simone here at NCAR and many other folks. So ozone depletion events are processes occurring in the Arctic which are related with heterogeneous recycling chemistry. During these ODEs, oops, right there, okay, there it goes.
You can point, yeah.
Yes. So during these ODEs, there is a strong depletion of ozone from background levels of about 30 ppbs, for example, to sometimes to detection limits, almost zero, mostly during the spring. And this are the records of ozone levels during the Mosaic campaign that was on board of a ship going to the North Pole. And during these events, it is well known that halogens play a very active role. So there is a process called or simplified as a bromine explosion. And in these processes, high levels of bromine monoxide, and also we know that iodine also plays a large role, and they dominate the ozone depletion during those processes, mostly during the spring. So what we wanted to answer was, okay, so if that's happening widespread over the Arctic, what's the impact when those air masses go into the northern mid-latitudes? So for doing that, we used the polar halogens module we developed a few years ago in Camp 4. This scheme or this module has 3 additional sources of halogens arising from the Arctic sea ice. One is the photochemical release of bromine and chlorine, which is mostly arising from the first-year sea ice after, photochemically driven. And then the other one, the second one, is the brine diffusion of iodine produced, biologically produced underneath the sea ice. And then the third process is once all these species are emitted to the atmosphere and the partitioning between all the halogen reservoirs and reactive species, they can be trapped by sea salt aerosols or deposit over the snowpack, and then they can photochemically recycling, and which constitute the third process, which adapts to what we normally call our halogen emissions, which considers basically only oceanic emissions of halocarbons and molecular iodine. So these processes, which are quite complex, we just parameterize them as good as we could for a global model. And this includes many fields that are that we keep track in the model and with the coupling of the ocean and with the ice. So one of the parameters, the most important one, is the changes and the seasonal changes in the first year and multi-year sea ice coverage, occurring in this case over the Arctic. Also, we need to consider the net solar irradiance reaching the Arctic surface for the different time periods, and we compute that using the cosine of the solar zenith angle, and this is shown here on the right for different seasons. And then, for sure, we consider the instantaneous surface air temperature and the deposition of the halogen species at different grid points, particular over ice. And then it's really important to keep track of the chemical partitioning between reactive and reservoir halogen species, which in turn depends on the background NOx levels and air pollutions that we have. So another question we wanted to answer was if the impact of halogens from the Arctic has changed from the pre-industrial period to present day. So these are our model experiments. In next results, I will show always results, the no halogen simulation, that means the standard CAM-CHEM chemical mechanism is shown in gray. Whenever we add halogens, that's a typical configuration that we usually work with. We include the oceanic emissions, which will be shown in blue. And then when we consider both the oceanic plus the sea ice emissions, I'll show those results in red. And we will consider two different bands, the Arctic latitudinal band. This is pointing like to the side, okay. So the Arctic latitudinal band, which goes from 60 degrees north to the pole, and an equivalent, a region, sorry, with equivalent area, which is from 47 degrees north to 60 degrees north, okay, which has the same area as the polar cap. And we perform 5 years long cyclical simulations for the present day and for the pre-industrial period, considering for each one of them the lower boundary conditions, the sea ice conditions for each of the periods, but forcing with meteorological fields from present day, okay, from a previous simulation, and using the low resolution, the 2 degrees horizontal resolution and 26 vertical levels standard in CESM1. So, and for the validation, we basically compare with two different type of data sets. One is the climatology of the ozone zone climatology from TILMS 2012, which recognizes the different behavior of Arctic ozone on the northwest and on the northeast. Okay, and I will show that a little bit later. And also compare with some observations, surface observations from NOAA and from the EVAS database at different locations, which are shown there in the map. So moving into the results, here on the top left, the panel A, we can see that the observations are in black with the hourly variability on each of these error bars on each of the black lines. And then the model results for the no halogen simulation are in gray, for the oceanic configuration are in blue, and for the one including the sea emissions are shown in red. So we can clearly see that observations, the minimum observed during the spring, the minimum of zone observed over the Arctic during the spring in the West Arctic is only captured when we include these sea ice emissions. We can also see that on the vertical profiles of the ozone zones, when we do the average during March, April, and May, I mean, in the free troposphere, basically, it doesn't matter if we use the oceanic or the oceanic plus ice simulation. The vertical profiles is more or less similar, but both of them show better agreement with observation compared to the no halogen configuration. But then close to the surface, this perhaps the model overestimate a little bit the reductions in ozone, but then it's the only way we can capture some of the values at the surface using this scheme. If we move to the East Arctic, we can see that basically the three model configuration are overlap. The more halogens we meet, the less ozone that we have, but they more or less show the same seasonal cycle, and the model reproduce that well. So in the central panel, we can see the surface ozone percentage change and the latitudinal variation of the ozone change. And we can see that there is a pronounced latitudinal gradient, which can affect regions in the northern mid-latitudes. And that's how we zoom in this next slide. Okay, so here we show, I forgot to mention here, so this is where the pointer. So the changes in ozone that I will show are the changes between the, the red and the blue simulation, okay? So now all the differences in ozone are between the red and the blue. And what we can see is that these Arctic halogens, the export of these low ozone and halogen-rich air masses from the Arctic can influence the background ozone level in North America and in Europe. And these lines over here show the percentage surface ozone changes within each of these regions that we have highlighted there. And it's about 5 to 6% in the northeast US and in Northern Europe, and a little bit larger if we consider the whole latitudinal band, okay, where we can have values up to 11% reductions when we include these Arctic halogens on the monthly mean. So to compare these results in the latitudinal bands I mentioned before, so in this light blue are the Arctic latitudinal band, where we can see a maximum reduction of about 16 to 17 ppts, which is about 40% of the ozone, surface ozone in this region. If we focus on the northern hemisphere mid-latitude, that reduction can reach up to 11%, which are 4 ppbs on the spring monthly mean that we get in the model. And if we go into the northern hemisphere annual mean, this only represents 2%. So this is showing and highlighting that these Arctic halogens emissions are important on a seasonal and local scale, but I mean, it won't affect the global mean, but then on a regional scale, on the springtime, it is important. And why is that? Why do we have these springtime pools? And that's because emissions increase during the spring because of the opposite behavior of changing in sea ice coverage and changing in solar radiation reaching the Arctic when moving from winter to the summer, which both of them, they have the multiplication of those fields maximized during the spring. And then also because there is a pronounced change in partitioning between reactive versus reservoir species of halogens. These are the dots here, the blue dots for bromine and the red dots for iodine. On the right axis, this is a ratio of the reactive versus the reservoir fraction, which maximize for bromine during March and for iodine during April and May. And this is why on the second panel, where we compare all the chemical loss by families, we see that most of the chemical loss is driven in the Arctic region by halogens, and mostly during the spring. And most notably, the ozone difference, I mean, the change in the difference in ozone here. So the blue line is the contribution for the oceanic emissions of halogens, and the red bars, the red part of the bars, is the contribution of the sea ice emissions of halogens and how they both contribute to the total ozone reduction in the Arctic. If we move that to the northern mid-latitudes, so what's the main difference? So ozone destruction is not due to halogens. It's mostly dominated by HOX and NOx. But then during the spring, there is still up to 40% of the total reduction is also driven by halogens. So finally, we just compare how were these impacts between the present day and the pre-industrial time. Okay, and the basically answer is during present day, there is more tropospheric ozone, so then the absolute ozone changes are larger. But then during pre-industrial time, there is less ozone, but then there is also less NOx and less HOX, and then the partitioning is shifted to reactive species. So that proportionally, the halogens have a larger impact in pre-industrial time than in present times, which is also shown here. Okay, so the black line is the change, the ozone change during present day. The gray line is during pre-industrial time, and the red line shows that the difference is larger during pre-industrial than during the present day if you compare in relative terms. So this is our results. The main conclusions are that the regional export of these halogen-rich and ozone-poor air masses affect the northern mid-latitudes, and that these seasonal behaviors is only captured when we include these halogen emissions in the model. So thank you very much, and I'm happy to take some questions.
Are there any questions? Please come to the microphone. I do have one while you line up, maybe? I don't know. It looked like you had a question. Okay, I just have a question in terms of this is really important, and I think, does it require VSL chemistry, or do you just need somewhat emissions that we add to the model framework? So do we have to have a certain configuration to implement that in the current model version?
So yeah, actually, yes, the halogen emissions from the sea ice are computed online. So it's not an offline set of emissions that we can implement. Like the halogen development, we have offline emissions of halocarbons and then online emissions of oceanic iodine, and then these sea ice halogens are also completely online.
So we could basically, it does require the halogen chemistry though?
Yeah.
Yeah.
Yeah, it requires the halogen chemistry to be active. Yeah.
Very nice talk. So you have a polar module, which is specialized to get the right amount of emissions in the high latitude regions. And you showed only the Arctic today. Now, do you use the same polar module for the Arctic as you do in the Antarctic? And what's the difference between reactive halogens between the two regions?
So that's a great question, Doug. So yes, we use the model. We have the polar module actually works in the Arctic and in Antarctica. CamChem overestimates quite much the absolute levels of ozone in Antarctica, over Antarctica. And we haven't been able to reproduce exactly the observations that were shown for ozone. I mean, we have the polar module validated with all the reactive halogen species, both in the Arctic and in Antarctica, but because of some additional reactions missing or some transport issues missing in the model does not reproduce well ozone over the Antarctica. Okay, and the partitioning is different. It's much more different because in Antarctica, in the southern hemisphere, there is much less NOx, and then everything, all the halogen is more partitioned into the reactive phase, so it's proportionally more efficient destroying ozone in the in Antarctica than in the Arctic. Okay, that would be answered.
And we move to our next speaker, Ben Gobert. He will talk about investigating the role of chemistry on the methane budget in emission-driven methane simulations.
All right, good morning, everyone. I have lots to cover, so. So this was funded by NOAA, and it's a collaboration with University of Arizona. Especially Amin has been doing a lot of the work, and we're using the short-lived halogen from Rafa, Doug, and others. I'm using methane emissions from a various product, especially NOAA. So the goal is to do emission-driven simulation, is to use emission-driven simulation of methane, so we can represent the emission, the chemistry, and the climate feedback, understand the methane budget, evaluating the impact of chemistry and chemistry change on the methane growth rate, include chemical feedback, and include various processes between those emissions and chemistry. Chemistry climate models do overestimate OH, they have larger uncertainties, and people have been using messy chloroform inversions. Instead of chemistry climate models, we tend to even disregard chemistry climate models, even though we do represent a prognostic OH, representing all of these different processes, including many chemical reactions. And so we want to reconcile those estimates. And there are also issues on the latitudinal and temporal distribution of OH, which I'm going to get into. So one of the things is the underestimation of CO. There are many, many papers, and it's not really understood why it's going on. And so this is an older one. This is the most recent one, where IR Chemic, which is one of the most recent intercomparison of chemistry climate models, here compared with CO measurements from Greenland ice core, is showing that not only we overestimate OH, and though we underestimate CO, we have been doing this for the entire record. So here I'm using the newly implemented CESM 2.2 short-lived halogen representation that Rafa Fernandez developed. Paper is in preparation. And we've been contrasting this with the Mozart TS 1.2, the standard chemistry of CESM2. And we did contrast those simulations in prescribed using the CMIP6 methane concentration fields, and 3 other simulations using 3 different emission inventories, and we contrast them all, so you get a double of chemistry and emissions and prescription in all of them. This is 5-year simulation to look at 2016-2018 results with ATOM observations initially. So if you look at ATOM OH with and without halogen, you improve OH, especially in the winter and spring of the mid-latitude and the high latitudes. And we do reduce ozone, and this is a non-result of the impact of halogen representation. It just wanted to take advantage of the OH observations during ATOM here. So if you look into the latitudinal distribution of land versus ocean and the surface versus tropospheric differences, you can see that OH is reduced mainly over the ocean and over the troposphere, and with some increase of the secondary OH sources over land, which tend to compensate. And that we reduce slightly more OH in the northern hemisphere, so we don't change the interhemispheric ratio, which is very important for as a metric of mesichloroform OH proxies. And the mechanism is a reduction of ozone, which gives you a reduction of ozone photolysis, primary source of OH, and the secondary ozone recycling of OH through HO2. And the net would be mostly a reduction of OH over the ocean and increase over land. So in terms of methane loss, in our default, we have 573 teragrams of methane per year loss for 2017. In the TS1.2, if we're using emission-driven, we have a range of values from 561 to 573. And when we introduce the SLH, we move on to 504, which is more, those 3 different simulations have the same thing, which shows that there is less spread with methane emissions. And this one has higher methane emissions, leads to higher loss. And so it's typically around 500 for the methane plus OH, and an increase from an increase by 16 teragrams for the chlorine sink, which gives you 520, and a methane tropospheric chemical lifetime increase by around a year. And now if you do another sensitivity where you use a different set of CO emissions, you can have up to 9 teragrams of methane change, which is mainly appreciated in emission-driven simulation. So Wild et al. Did lots of sensitivity of comparison of tropospheric ozone burden versus methane lifetime, where they look at emissions, isoprene emissions, lightning NOx, and deposition, and other things. So I wanted to redo this plot, looking at in the light of the halogen chemistry. And so from here, we move on from a high ozone, although in line with the tropospheric ozone burden estimate from TOR1, which is observationally based, and methane lifetime here. So good ozone, but underestimation of methane lifetime. And with the halogen now, we move here, where we underestimate ozone burden, but we do have a better lifetime. And then this sensitivity is the lightning NOx, which has been shown to be the most important parameter for methane lifetime in CSM in this paper, that red line here. So this is a conundrum. We should be using these in the way we define the new chemistry for future simulation. So it keeps going. So now I did 20 years simulation where I'm comparing prescribed versus emission-driven using the new carbon tracker methane released posterior emissions, where they're using, I should say, they're using isotopes to constrain both the total methane emitted and the partitioning between the microbial and fossil fuel sources. So here I'm using Mopit. I've been decomposing the time series, and so now we do have underestimation of CO in the northern hemisphere that is not as bad as before, and an overestimation for tropics and southern hemisphere. And if you look at the interannual variability, you can see that we are actually reproducing very well the changes that are mostly due to fires if you detrend, and that the field emissions are actually very good at representing those. Although sometimes we do have fires that are not in the record, and sometimes some fires in the Arctic 2021 is not well represented here. But if you look at the seasonal cycle, we now overestimate CO, which means that we still have work to do in the spring, and but we underestimate CO during the summer. So there's still a lot to do on photochemistry, secondary sources, representation of especially emissions from fires, biogenic and anthropogenic sources. Here is GOSAT methane observations that only started in 2010. We do now better represent methane in the emission-driven than in the prescribed simulation run, which is kind of interesting because especially over this period, the methane is supposedly prescribed by observation. So it really has to do with the spatial distribution of zonal mean methane emissions versus having actual 1 by 1 degree maps of monthly emissions. We do see that the impact of the overestimation of the underestimation of OH in the southern hemisphere has an impact where methane is starting to grow too much, and actually reverse the errors. But overall, it's similar performance or better in emission-driven for the methane observations comparison. This is showing the same thing for aircraft in situ profiles for HIPPO 125, ATOM 124, so for the, but arranged by season and from different latitudes, latitudinal bands, and you can see the same thing where we tend to do better in the northern hemisphere, but then having a overestimation in the emission-driven runs for the southern hemisphere. And so this is consistent with both GOSAT and Mopit for two different campaigns that were made mainly over the ocean. If you look over land, so these are two different campaigns that were based out of Seoul in South Korea and then go flying around, especially Eclipse was flying over the ocean, and so in the open ocean. So this is representative of actually East Asia. And we do better in the emission-driven, although we tend to overestimate the local emissions from South Korea. But this is really, it looks really good compared to observations. So we do have a higher burden in the CSM methane, as shown to be better with GOSAT. And this translates into a higher methane loss, which means that our system is, with our OH prognostic array, is actually well buffered and tend to dampen the methane perturbation so that the differences between the two runs are not as large and would give you a methane lifetime that would be similar between the two. So, in summary, our updated representation of CSM2 allows us to better represent simultaneously a better ozone, OH, CO, methane, and other related oxidants, as shown by aircraft observations and satellite columns of CO and methane, as well as NDAC, that didn't show here. And that we do now overestimate CO in the spring and underestimate in the summer, and we overestimate, we do have a better OH in the northern hemisphere, but that comes at the cost of more work to be done in tropics and the southern hemisphere. And so we can now do emission-driven simulations that are better than the prescribed one, and that our methane chemical loss, especially through secondary OH sources that are modified in the halogen representation, is much better and well buffered compared to perturbation, and so we will look into OH trends next. Thank you.
Nice talk, Ben. So can you go to the vertical profiles, the comparison with the air quality, yeah, that one. So you say that the emission-driven overestimate a little bit. That's for year 2022 on the right. But then, if I don't remember wrong, your plot, your trend on total methane emission for the emission-driven simulation also overestimates moving into the latest period of the simulation. So is this local or this is global overestimation? It's very local.
Yeah, this is over the entire latitudinal band. So yeah, we do tend to underestimate towards the end of the record, for sure. Yeah.
So based on your emission results here, are you suggesting that CMIP7 should emit methane instead of
CMIP7 emission? I've not done that yet. But that would be next step, and fire emissions.
Yeah. Yeah, I think after in the discussion we can talk a little bit about what simulations we want to aim forward. Maybe that would be another point to discuss. Is there any more questions? Else we welcome our next speaker, Chuan Feng. Is that right? Yes. Okay. Again on methane, distinct efficacy of regional emissions in affecting global methane concentration. I guess I should go to the microphone. A global modeling study with interactive methane chemistry and emission tags. Go ahead.
Good morning, everyone. Sorry. My name is Chuan Feng. I'm currently a postdoc at Texas A&M University. It's a great honor for me to present our recent work titled Distinct Efficacy of Regional Emissions in Affecting Global Methane Concentrations, a modeling study with interactive methane chemistry and emission tags. This is a collaborative work with Dr. Yang Xu from Texas A&M University, Dr. Benjamin Galbert from NSF NCAR, and a PhD student, Muhammad Amin Marizai from University of Arizona. So methane is the second greatest anthropogenic greenhouse gas. So understanding the impacts of its regional emissions are crucial for effective methane mitigation strategies. So in our study, we run two sets of simulations, the baseline and the no emission simulation. They all cover the years from 2014 to 2019, and they use the improved short-lived halogen chemistry, and the methane emission data we use is the GCP 2020 posterior data. And for the baseline simulation, we include tags of the total emission, Asian emission, Europe emission, and the North American emissions. We will talk about this later. And all those simulations are using setup by Marizai et al. And this study is following previous presentation by Dr. Galbert. And the LCLH chemistry is based on the work of Dr. Fernandez, and the GCP data is the work of the team of Dr. Sanos. So this figure shows the difference between the default CESM model and our emission-driven model. This shows the surface concentration of methane, and it's obvious that the default model, there is no longitudinal variations, and our emission-driven model shows clear spatial patterns. And we compare our model simulations to the observations in these figures. Panel A is showing the a global map of the correlation between our simulation and the ground observations. And the panel C and D are zoom-in maps. And the statistics in panel B shows that most of the correlation are greater than 0.7. And the bottom panels here, we show our simulation in orange color, and the default CAM-CAM simulation in blue, and the observation data are in black. So this result shows that we have good agreement with Global In-Situ Observation Network. And the observation data we use is the NOAA Methane Global View Plus, the OBSPAC data. And the key innovation in our research is the tagging technique. So this technique draws inspiration from studies on aerosol and CO transport and chemistry, and enables attributing methane to different emission sectors and regions. By tracking each methane tag, our approach provides insights to the contribution to the atmospheric burden at specific locations and times for each tag, accounting for spatial and temporal characteristics of related chemical processes. And specifically, in addition to the baseline simulation with total methane emissions from all regions, we implement regional emission tags for Asia, Europe, and North America to quantify methane concentrations attributed to each source region. So this figure shows how the model works, how the emission-driven feature works. Firstly, we got the total emission data. Then based on that, we create the emission data for each tag. For example, in the middle column, this one is the emission data for Asia, emission data for Europe and North America and other regions if needed. Then the model reads in this emission data, and after transport and reactions, the model outputs the concentration of the tags on the right. So the first panel shows the concentration of methane from Asia, and the second one shows the concentration of methane because of the emission of Europe, and the third one shows North America. So we got the time series of the methane tags, and in this figure, the simulation from the no emission run is plotted in black dots. And the relative growth of global mean methane concentration compared to this no emission run is plotted in color. The green is the European tag, the red is the North American tag, orange is the Asian tag, and blue is the global total concentration. And we noticed that Asian has the greatest increase in global mean methane concentration because Asia has the strongest emission. But our question is, do they have the same efficacy in increasing the global mean methane concentration? Or in other words, if we have a megaton of methane, is there any differences if they are released in different regions? So here we define the term efficacy of methane emission. It is the increase in atmospheric methane concentration per unit cumulative methane emissions since January 2014. And the equation is shown here. This is the efficacy, and the C tag is the concentration of the tags here, and the C0 is the concentration from the no emission run. And here it is the cumulative methane emission since January 2014. And the unit for this variable, the unit for this variable is ppb per megaton of methane emission. Here is this equation again, and we plot each term in different panels. This is the relative growth, or the numerative, or this one is the denominator in this equation. And the third panel is the efficacy. Because of the definition of the efficacy, there is a accumulation term here, so they are descending as time goes on. But we noticed that the efficacy from Europe is the highest among all of them, and which means the methane emission from Europe has greatest efficacy. And in panel D, we we plot the ratio between the regional efficacy and the global efficacy. So the global efficacy here is 1, and we notice that the efficacy from European emission is around 20% stronger, higher than the global. On the right, we plotted the map of the efficacy. The first column is showing the result using data from 2014 to 2016, which is the first 3 years, and they have higher values of efficacy. And on the right, it shows the result using 6 years data. The first row shows the global efficacy, total efficacy, and the second row shows the efficacy from of Asia emission. The third one is the European emission, and the last one is the efficacy of the North American method. We noticed that the European emission have the highest efficacy, and also the regions nearby the sources are under the greatest impact. Also, we noticed that the European emission have a greater impact over the North Pole regions. So why is European showing greater efficacy? We suggest it is probably because of the methane lifetime are different among different regions. So in this equation, it shows the methane concentration following exponential decay, and the lifetime is here in orange. And with our simulation data, we can estimate those lifetime. And the result is shown below in orange. And we notice that the European is showing a much longer lifetime than the other regions. So that makes us think what causes the longer lifetime of methane from Europe. We know that the methane concentration is the highest near the source regions, and then after emission, it will decrease due to transport or dilution or reactions. Therefore, the grids of the values where the values are higher than the 90th percentile, it's giving us information where the most methane molecules are located at. So first, in this figure, we plotted the distribution of all the tags, and we marked the 90th percentile for each tag. And in the panels down here, we plot with the white line, we plot the 90th percentile value. For example, in panel C, this is the 90th percentile value in this white line, and the value is higher than that is within this region. We noticed that after emission, a large amount of methane from Europe are transported to the North Pole region, where the concentration of OH radicals are very low, and this results in a longer lifetime of methane emission from Europe. So in summary, we utilized the CESM2 with emission-driven methane feature, short-lived halogen chemistry, and tagging technique, tracking 3 respective representative regions. We conducted the 6-year simulation, and the simulated concentration shows reasonable agreement with observations. We estimated the methane lifetime and found that the lifetime closely reflects the OH concentration along the transport pathway after emission. And European emissions have the greatest efficacy in increasing the global methane level, mainly due to their prolonged lifetime over the polar region. However, the radiative forcing from Europe is not necessarily higher due to the weaker solar radiation over the high latitudes. In the future, we plan to work on the diagnostics of radiative forcing for the tags, and we plan to run longer simulations. And in the end, we acknowledge the funding from Spark Climate Solutions and also the computing allocation from CISL NCAR. And also thank NCAR for the traveling support. With that, I'd like to answer questions. Thank you.
Other questions? Yes, Aline.
For the really interesting talk. I'm wondering if I understood correctly from your slide, you're actually seeing a shorter lifetime from North America than from Asia? Did I catch that right? I thought I saw 12 years and 10 years, but maybe I mixed them up. But I'm curious if you have thoughts on why the lifetime would be shorter from North America in contrast to Asia.
I think this is just an estimation of the fitting, and the fitting is very sensitive to the parameters. So maybe the length of the simulation and the emission and even the F term here may have an impact. So these two numbers are very close to each other. So we are not 100% sure that they are accurate enough to compare between these very close numbers. But I think we are more confident when comparing a longer lifetime, such bigger difference like this. So thank you for the question.
Hey, our next speaker is Jiandan, is that right? You? Diagnosing the UH response to ENSO and its underlying drivers. So, looking forward to it.
Okay, thank you for the introduction. I'm Qingdan Zhu. I'm right now an MIT postdoc, Houghton postdoc fellow working with Arlene. And today I would like to present our work on the chemistry-climate interaction that focuses on the OH chemistry. And we really want to diagnose further into the underlying drivers of how OH respond to ENSO. So I think the two talks before me have already said a good introduction to my work. So we'll also focus on this mystery on interpreting these historical methane trends, given that the methane is a potent greenhouse gas that's second only to carbon dioxide. However, compared to the methane sources, the methane sinks is pretty much dominated by the reaction with hydroxyl radical or OH. So the reaction with OH alone will attribute to approximately 90% of the total methane loss. Therefore, interpreting this historical methane trend is not possible with the constraint on the OH itself. Lacking direct OH observations, the OH is normally indirectly estimated using the inverse modeling that constrained by the long-lived species such as mesochloroform. So right now in the current studies, some studies suggest that this interannual variation in the OH anomaly are in part related to the ENSO variability. So here I show one study while the line represents the methane chemical loss, so you can view it as the parameter proportional to the inferred OH. And the different lines represent the two different inferred OH constrained by two different mesochloroform observations, and the shaded color represents the ENSO index. So from this figure, you can tell that this inferred OH itself embeds a very large uncertainty, and the signal with ENSO is quite noisy. And the investigation between OH and ENSO is also studied in a cleaner manner using the model simulation in absence of the external forcing. For instance, in Turner et al. 2018's paper, they present these thousands of the OH measurements without any external forcing. And what they find that is the simulated OH is not just the white noise process, instead ENSO is the dominant mode of the OH variability. However, there remains a lag in the mechanic understanding of why OH is changing along with different ENSO phases. So if we look back to these OH chemistry diagrams, we can have multiple hypotheses that lead to the OH response to the ENSO from both the OH production side as well as the OH loss side. For instance, under the different ENSO phases, we will envision some changes in the meteorological factors such as cloud cover, moistening, as well as atmospheric circulation. All of these factors will affecting these different parameters that involved in one of the OH production pathways that I denoted here. And also, there are studies suggesting that the lighting NOx emission will also be changing under different ENSO phases, which will contribute to altering this another OH production pathways through the reaction between HO2 and NO. But also on top of that, from the OH loss pathway side, we will also envision the changes in the BVUC emission as well as biomass burning emissions under during the ENSO phases that will contribute to altering the OH loss pathways by reacting with the non-methane VOCs as well as COs. But on top of that, among all of these different drivers, what we still don't know yet is how these different processes are interacting with each other. Are they offsetting or are they amplifying this OH response to the ENSO? Therefore, in my project, we really want to address two major questions. First of all, can we detect these robust changes in the OH during El Nino and La Nina compared to the neutral conditions? And also, what are the roles of these different driving mechanisms? To answer this question, first of all, we can posit the SST patterns under the different ENSO phases using these 13-member initial condition CESM 2 Wakan 6 model ensembles. For each ensemble member, I calculate the SST anomaly by subtracting out the ensemble average of SSTs, and I also calculate the corresponding Nino 3.4 index. And using these Nino 3.4 index, I can set out the boundary and the threshold that can categorize the SST patterns into the different three ENSO phases, including El Nino, neutral, and La Nina conditions. I can further step up the categorize the SST pattern together, average them over, and get these climatological SST patterns during both El Nino, neutral, and La Nina conditions, shown as a map in the at the bottom. With these prescribed calculated SST patterns, I can attach them to the SST pattern climatology for year 2000, and I run 3 different CAM model simulations that are prescribed by these 3 representative SST patterns. And for each simulation, I run the model for at least 7 years to assess the impact of the atmospheric variability. And in CAM, the model itself is by default configured with the interactive lighting NOx parameterization that are based on the cloud top height, as well as the interactive BVUC emission scheme that we normally use the Megan schemes. Therefore, I further conduct this mechanism denial experiment by turning off the interactive BVUC schemes, as well as the these lighting NOx emission schemes. And using these MET-only scenarios, I can further diagnose the drivers of the OH chemistry to respond to ENSO only from these meteorological factors. And by contrasting the first two scenarios, as well as the last 2 scenarios, I can further diagnose the impacts solely from the lighting NOx emission and the BVUC emissions. And also for all our model simulations, the biomass burning are prescribed using the SAS emission inventory, so the biomass burning impact is not yet discussed in this talk today. Okay, so now I will show you some results. First of all is this MET-only scenario analysis. What I'm showing first is these changes in the water vapor during El Nino and La Nina compared to the neutral conditions, and I narrow it down to -30 to 30 latitude beams. That's where the most changes occurred, and the changes elsewhere are relatively small. And I also further dotted the regions with the significant changes at the 90th confidence level. So as you can tell from this map, we do observe these changes in the OH water vapor along with the changes in the SST anomalies following the Clapeyron-Clausius equations, whereas the water vapor tend to increase over the tropical Pacific and decrease during El Nino and decrease over the same region during La Nina. And in addition to that, I'm also showing these changes in the cloud cover, both during El Nino and La Nina compared to the neutral conditions. And these changes are primarily driven by the shapes of the convections. For instance, during El Nino, the convections have been shifting towards the central and the eastern Pacific. That's where you see the enhancement of the cloud cover over the same region. And the convection tend to compress over the tropical Pacific during the La Nina events. So these were showing the changes in the meteorological factors, and next I'm showing you the changes in the water vapor. So in this map, I'm showing the changes in the OH also during El Nino at the top and during La Nina at the bottom compared to the neutral conditions, and the dotted region were showing where the changes are significant. First of all, at the global scale, actually we don't see the significant changes of the global air mass weighted tropospheric OH columns. However, at the different regions, we do find some significant robust signals. especially over the Indonesia. During El Nino, we find that the OH will increase by up to 7% over this region. And comparing between El Nino and La Nina events, we find these robust opposite changes in the OH over Indonesia region as well as over Tropical Pacific. So these were the changes in the OH, and in the next slides, I will dive into the OH budget and try to diagnose why the OH is changing, shown in the previous slides. So what I'm showing first is during El Nino, the changes in the OH production rate at the top and the changes in the OH loss frequency at the bottom. From this map, you can easily tell that the changes in the OH is pretty much dominated by the changes in the OH production rate, while the OH loss frequency stay relatively constant. If we zoom into this Indonesia region and then further calculate the contributions of the individual OH production pathways and the OH loss pathways, we find that during El Nino, the total OH production rate will increase by up to 11% over the Indonesia region, and over half of them were actually attributed to these primary OH production pathways that consist of the photolysis of ozone followed by the reaction with water vapor. And if we further dig into what the individual parameters are driving this increase in the OH primary production rate, we find this competing offsetting process, and it's actually the result of about 16% increase in the ozone, along with about 4.3% reduction in water vapor. Even though we observe the significant changes in the cloud cover, we don't find the corresponding significant changes in the geosingle D, so the ozone photolysis frequency. So next, I'm moving to the lighting NOx emissions. What I'm showing first is the changes in the lighting NOx emissions also during El Nino and La Nina, and then mask out all the regions where the changes are not significant. And as you can tell from this map, only this Tropical Pacific, over the Tropical Pacific, you can see these robust changes in the lighting NOx emissions under different ENSO phases. However, if you look at the global scales and also include the changes of the lighting NOx emission elsewhere, you will find that this large variation in the lighting NOx emission that are primarily driven by the atmospheric variability over the land. And this is because the lighting NOx emission production over the land is over 1 order of magnitude higher than it is over the ocean. So even though we see these robust signals of the lighting NOx emission changes over the Tropical Pacific, it's overshadowed by the large variation led by the atmospheric variability from the land. That's why if we further look at the changes in the OH, these changes in the lighting NOx emission during the ENSO actually leads to insignificant impact on the OH, both globally and locally. And last, I'm looking into the BVUC emissions. Unlike the lighting NOx emission, BVUC emission, we do see some of the robust significant changes under the different ENSO phases, especially over this tropical South America. So during El Nino, we find that the isoprene emission will increase by up to 8% during El Nino and decrease by about 2% during La Nina. And looking into how it's affecting the OH concentrations, what we find here is over the tropical Pacific, during El Nino, the OH would decrease by about 3%. However, during La Nina, we don't see these significant changes in the OH, along with the changes in the BVUC emissions. Looking into the OH budget analysis, these are what we were showing the changes in the OH production and the OH loss frequency during the El Nino, and we find that the changes are pretty much dominated by the OH loss frequencies. And zooming into this tropical South America, we find that the OH loss frequency will increase by up to 8.4% over this region, and is primarily dominated by these OH reactions with isoprene, along with about 17.5% increase of the isoprene concentrations. So to wrap up, in these studies, we want to focus on the interconnection of the interannual variability of the OH and the ENSO, and we want to diagnose the drivers of these OH changes under different ENSO phases, including the meteorological factors, lighting NOx emission, and BVUC emissions. Even though at the global scale we don't see the significant changes, we find that these different drivers does lead to pronounced OH changes at different regions. And also, as I mentioned in the introduction, the different ENSO phases will also lead to the changes in the biomass burning. That's why in the future work, we want to further look into how these changes in the biomass burning will also affect the OH budget. I will end here and happy to take questions.
Hi, nice talk. So I guess you were showing the annual average maps, and all the analysis are based on the annual data. I was wondering if you have also looked at the seasonal, like summertime, and if it matter at all.
Even though I'm only showing the annual changes here, we've been looking at like the monthly variations of the OH, and we even look at how the OH is responding to ENSO at near the surface or in the upper troposphere. So both seasonally and vertically, we find pretty much similar results as the annual OH response.
I guess I'm curious, like for the isoprene response, then does it also leave then a fingerprint in the ozone and the carbon monoxide that's being generated from the isoprene increases? Like that, and are those realistic, I guess? I'm curious.
Question. So if you look at this OH budget analysis here, but it's only focused on the Chaco, South Pacific, America, you find the most changes are these like instantaneous increase in the BVUC concentrations. But yes, if you look at the larger domain, I would expect also some of the changes in the CO that along with the increase in the isoprene emissions. But the changes is not like very robust, very significant in terms of the OH budget. But we were looking to the CO budget as well as the ozone budget, given all the model simulations are saved out there.
Any other questions? Is there anything online?
Thank you.
Okay, later. Thank you very much, and we'll talk more about this OH and methane lifetime, everything in our discussion. But before that, we have our last speaker, which is Sean Honemekel online. And he is talking about the CSM chemical forecast, a summary of capabilities, and what's next. Okay, thanks, Sean, for joining us online, and please go ahead. We don't hear you yet. Maybe, I don't know. Have to unmute.
Let me try here again.
Now we hear you. We hear you now.
Okay.
Great.
My video looks, or slide is up there.
Yep.
I'm gonna just talk about the CESM chemical forecast system that we do in ACOM, and I'm just gonna overview a summary and some of the coming changes to our forecast, and also just want to highlight the team that also contributes to our forecast, and Simone and Rebecca and Louisa, who are all there, and then also our IT pros, Garth and Carl. And this is just a quick little demo of what our forecast can do. This is just a loop of CO fires from the beginning of the month, kind of highlighting the Canadian fires that have been going on. And so this is just one of our pre-visualized forecast products. And another example, this is another version of our Wacom CO Fire product, just overlaid on our ACOM Worldview product, which is kind of an offshoot of the NASA Worldview viewer. Similar depiction of the Canadian wildfires. This one's from specifically June 1st, and it shows the Wacom CO Fire forecasted product in the white box, and it's overlaid with the errors, Aqua Airs CO up in the middle, troposphere. And it's just kind of a nice example of how you can sort of merge these two products together in the world viewer and sort of visualize what's going on. And so just to overview what our forecast system is under the hood, we utilize CSM 2.2.2, and our comp set is the Wacom Specified Dynamics FWSD comp set, and we do 10-day 0Z forecasts every day, and we've been doing these every day since 2019. And there's actually 2 parallel runs that we do, and the only difference between these runs is the biomass burning emissions product that's fed into it, one being FIN and the other QFED. And these both run on a 1 degree horizontal grid, the Epson finite volume grid at 88 vertical levels, and there's just a little depiction there of the vertical resolution that hopefully you can see. And our levels cover the surface to the thermosphere, and we get about 1.2 kilometers resolution in the UTLS region, 1.2 to 1.5 in the middle atmosphere, and below that I think it averages out to right around half a kilometer or so. And this is driven with the NASA GEOS FP product, and we are nudging it with TU and UV winds, and the current anthropogenic emissions package that we use is CAMS version 5.1. And this is just a breakdown of the system and how it runs. And so the way we have this set up to run is it's a bunch of different tasks chained together using PBS Pro. This way we can predetermine the resources that are utilized for each task, and we get the added benefit of efficiency with being able to chain the job so that as soon as one task is done, it automatically starts the next task or tasks. And the model, of course, is run on Derecho, and then everything else is run on Casper. And the system can be called via the terminal if we need to run a specific day or run a specific task, or just set it on a cron to let it run automatically on its own, which is what we normally would do every day. And so just some of the individual tasks here, we download and regrid our meteorology. We do our biomass burning emissions with QFED or FIN and update those emissions. We set up the XML files automatically in the software to run the model and then run it. And then all the post-processing is done after that, where we convert to pressure, calculate any additional quantities that we need for our forecast, and do all of the plotting. And then all that information is archived and distributed as needed. We distribute to several different locations and plot a few different things, which I'll show here soon. And then there's a cleanup process that keeps everything nice and clean, since we run this on a scratch space. There are some challenges that come along with doing this. One of our major bottlenecks are the meteorology downloads. These are 10-day forecasts, and this equates to 818 files that we have to download every day. And in total, that comes out to about 243 gigabytes worth of information. And server slowdowns are not uncommon. So we have to deal with that quite a bit. There's also the usage of computer resources. We use about 20,000 core hours a week, which by itself isn't a significant amount, but that does add up over time. And we do share those resources on the account that we use. And so that can be a challenge from time to time. And then, of course, when we get to the end of the fiscal year, people competing for resources, that can also pose a challenge. And that ties into our time constraints because we do need to finish our forecasts in a timely manner. Since it's cumulative, today's forecast always relies on yesterday's forecast to use as an initial condition. And there's the added complexity with larger runs such as Musica, which can take much longer to run. So we aren't necessarily able to do a 10-day forecast if we're using Musica. And then there's some other things like keeping up with the emissions inventories. They're always updating them, and we only keep we have to run them out ahead of time to keep them in the future. And we only do so much of that at once to keep the file sizes from getting too large. And then there's hardware and software changes and downtime, which I'm dealing with currently. And so how these are getting used, one of our primary use cases right now is it gets used pretty heavily as a boundary condition for regional runs. We do this with our own ACOM WRF-Chem forecast that I also run. And there's other people that do this as well with their own WRF-Chem runs. We've used this forecast for field campaign flight planning. We have our own other software suite that we can actually feed our forecast into that allows us to flight plan. And we've used this as far back as in some various forms, as far back as Contrast in 2014, which I think is maybe kind of where the whole forecast system originally, I think, might have actually gotten its start, and then used it very heavily during ACLIP, and it's been used for occasionally with a couple of other ones. There's some external sources that use our forecast. This is an example is Resource Watch. They ingest our forecasts every day, and then there's all the other individual users that use it for various things to do comparisons, model studies, and do, et cetera. And all this information is available in a couple of different locations. One is the Research Data Archive. In their search bar, you can just search for WACM and it'll show up, but otherwise it's dataset 313006. And this is nice because we get a DOI assignment, which allows us to track publications at least to see how much it's getting used. And these are only the analyses, and they're usually a couple of weeks behind real time, just in case I need to do any reruns. And the second locations are our own ACOM forecast page. Also easily can be found with a Google search, ACOM forecasts. And there's a few different products in there to choose from. From a visualization perspective, there's our ACOM Worldview product, which I showed in my third slide. There's pre-plotted forecast maps like the animation I showed in the beginning as well. There's a custom plotting tool where you can go in and pick a date, a variable, a time, a location, and do your own map or vertical cross-section if you want. And then we also store the last year's worth of our analyses, and including the latest forecast outputs on our own server. And from there, you can download the full file if you want it, or a subset if you would like as well. And just a few statistics. Since we've first implemented it on our server, we've had over 17,000 direct downloads, over 900 unique addresses. And to the right is just the metrics from the Research Data Archive. And one thing to note there is our usage. The usage is almost quadrupled from 2023 to 2024, which is nice to see. And so the stuff is definitely getting used, and our usage seems to be continuing to rise, which is nice to see. And then bottom left is just some of the publications that are on the RDA's metric. And so the changes that are coming and our long-term goals with our forecasts, we're getting ready to make the model version change from CSM2 to CSM3. That'll be accompanied by a COMSET change, switching away from the specified dynamics version and into the newer nudged version. There'll be a vertical level change that comes with that, and look at the latest and greatest emissions, and we'll probably trim that from one model run instead of 2 parallel runs to make way for a Musica run. So we'll have a 1 degree at finite volume run, and then eventually a Musica run as well. And then doing some updates to the code base just to improve our downloading and make the code more flexible and get it ready for Musica, and some cleanup. And then once all that's done, hopefully I'll make it available on GitHub for anyone else to use if they want to use it. And long term, as I alluded to, we would like to move into the Musica framework and ultimately end up with one unified global and regional forecast system. And these are just a few other finer details from the last slide. Our changeover from CSM2 to 3 nets us quite a few improvements or in bug fixes and code updates. A few are just an improved dust scheme. We get Hemco. As we move into Musica, we switch over from finite volume to spectral element. There's the opportunity to go from CAM6 to 7. We can utilize the moving mountain gravity wave scheme. We go from MAM4 to MAM5, and then a whole host of other things. And then another wish list item will be to add in some diagnostics, evaluation, and some skill. And we have several options for that, such as the Atmospheric Model Working Group, Diagnostics Framework, or the ADF, and then Melodies Monet, which Louisa talked about a little bit ago. And so I think that's most of my time. I think I got about a minute left if there's any questions. Otherwise, thanks for listening.
Thanks, Sean. Are there questions to the chemical forecasts? Just maybe to add, if people are interested to look at specific variables when we're updating those forecasts, there are things that may not be necessarily included. I noticed, for example, maybe surface temperature even is also very interesting. There are other climate variables, other things that may be of interest to some people. I think we do want to look into that more, so if people have time to look at it and give input, that would be great. And yeah. So now I think we move over to some more general discussion again, and maybe we can bring back the first slide set again for that, what we had in the beginning, the morning slide set. So one thing, the theme for this afternoon, and that's great, for the afternoon was the UOH, and methane, interactive methane, and very short-lived halogens. And the question came up, can we run this in future development simulations? So just to iterate again from the talk, so the standard version, CSM3, CMIP7, I think at least what we know so far is there was a code freeze, and we're still developing the model. So most likely new developments will not go into those simulations. However, and we come back to the other things. However, our development really, if possible, continues, and we're hoping to put some of the new developments in a new model version. So one thing is definitely the TOVX scheme that is in progress. And then, as we said, the short-lived halogens and the interactive methane. The other thing is also the interactive fires, and I talked to Dave Florin, so maybe that will be some focus we want to look into to really have also, and another thing is the interactive CO2 emissions and fire emissions. There's a lot of more interactivity that we can put in the models and that we can get different answers. I think that will be really interesting and hopefully something we can all work on together as a community to contribute. So thoughts on that? Anybody wants to add anything or ask questions to our plans? And definitely it's good. I mean, yeah, Rafa working on it already to implement new VSL in the development version and then going over to CMIP 7. We are limited so far by the developments of CMIP 7. That needs to be finalized so we can get final simulations and experiments to get started. Okay. Yes, question.
Question about the methane emissions and whether interactive wetland is part of that model or what the plans are there.
I don't see, oh, there's Ben. Ben, do you have an answer for that? We don't hear anything, I think. So maybe you have to just go and speak in. There's another mic in the back, Ben. Maybe we can use that one.
Okay. So yeah, it's kind of lagging. There is no funding in CLM group to work on this. I've tried to submit some proposals, but yeah. It's offline mostly. Nobody has worked on doing the interaction with the atmosphere, but yeah, it'd be great to do it.
That want to work on that? That would be great. Or others are interested, and then, yeah. So something we need to put on the list, on our wish list for sure. Okay, then other things are what we had started earlier, or at least the discussion on the intermodal intercomparison MIPS. As I have a list here, if people are having any intercomparison projects they want to mention that are coming up, or any thoughts on those, where we are going, that would be great. There will be some discussions on CMIP 7 simulations in general and where we are going, which is at the moment not clear, depending on funding and other things happening. But we do, I think a lot of people are very keen on finishing CSM 3 and performing standard simulations, also contributing into these future MIPs, GeoMIP, AirCam MIP, and so on. So one thing, no matter what, that is already ongoing is the HTAP simulations, as I said before, and I went really quickly over it. Luisa and Rebecca are leading those, and if people are in the community interested to help with those, if people are interested to perform simulations and analyze them, that would be really appreciated. Any other thoughts?
Discussed yet, Doug or everyone, but for the VSL's MIP configuration, I mean, we will use CSM2 Wacom 6, but I remember the plan was using CMIP 7 emissions, wasn't it, on boundary conditions? So that will be possible. I mean, despite CMIP 7 projects are not continued using CESM3. So that will be possible. So those are ready? Yeah, okay.
Done, and so we are, I don't know if Doug even started the transient CMIP7 run or is about to when the computer comes back up. It just came back up.
Start it.
Interesting. Other thoughts? We are seemingly maybe being hungry for lunch, and people want to just have more discussions. But if there's anything else, please bring it up now. As we conclude this Chemistry Climate Working Group session for today, and yeah, thanks for coming.
Great. Hello, everyone. We're going to get started. So I'm Mike Levy. This is Leisha Bernadette. We're the software engineering co-chairs. This is the agenda. It's also available online. We only gave ourselves 10 minutes for this welcome, so we'll probably be running 5 minutes late, starting with the first talk, but we'll take that out of the discussion. We do want to highlight two things. One, Chris is here, so he'll be in person, not remote. And then the discussion is going to involve everybody. I'm going to be watching. I'm going to know if you don't say anything in the discussion. I'm going to hold it against you. So just a few other highlights. So Eric had a poster yesterday. I didn't realize the posters were all going to be taken down at the end of the session, but I'm sure he's carrying it around with him everywhere he goes. It's his little challenge token. Cheryl Craig is giving a talk in the 30th anniversary celebration later today. And then tomorrow at the end of the event, we're going to have a happy hour at the Rayback. We know there are a lot of people online that are local, but weren't allowed to pay a registration fee to come in person. So we're hoping we can actually get together in person. And so this is just like a mile east on Valmont.
Okay. Well, just to provide a few updates on what's going on in NOAA, and this is like a really big title, right? NOAA updates. We could talk about lots of things, but just in terms of Earth system modeling, we have been working over the last few years in the development of the UFS, the Unified Forecast System, which has a lot of touch points with the CESM, especially in terms of infrastructure. So UFS is a community model. It is supported by EPIC, the Earth Prediction Innovation Center, which is entity, it's a contractor funded by NOAA. And this unified forecast system can be used for both coupled global scale simulations as well as a limited area regional model. UFS currently only has one dynamical core for the atmosphere, which is the FE3 dynamical core. And as far as physics, it uses the CCPP, Common Community Physics Package, for interface with the dynamical core. And we're also bringing several simple atmospheric composition aspects like smoke, wildfire smoke, and dust into the CCPP for that connection. As far as marine components, UFS is using the MOM6, SCI6, and WaveWatch 3, so lots of overlap with what the CSM is using. Land surface models, we use the RUC for the short weather applications, but then the NOAA, NOMP, and more recently, we also brought the GFGL LM4 for those longer timescale integrations of the UFS. We're also connecting a number of fire and atmospheric composition packages, such as the community fire behavior model developed in great part here at NCAR REL, but also GoCart from NASA and CMAC from EPA. So then we use this set of infrastructure building blocks to create a number of applications, which are the apps, such as short-range weather for scales of hours to a few days. We have a hurricane application, medium-range weather out to a couple weeks, subseasonal, seasonal, air quality, coastal, etc. These applications are all in different levels of research and deployment into operations. So some are already operational at NOAA and SEP. So in addition to these component models, there are a number of infrastructure touch points with CESM and with NCAR and with CIMA, such as the CMAPS mediator, the CDAPS data models, ESMF for coupling, FMS infrastructure, that's part of some of your component models. And also, we are exploring the inclusion of MPAS-A dynamical core. I'll talk more about that later in my talk, but we've been greatly inspired by the multi-die core infrastructure in the CSM to implement this. So just a few highlights of things that happened in the UFS in terms of deployment since the last workshop when I was here giving an update. The HAFS, which is our hurricane analysis and forecast system, with the new version is going to be implemented in operations now next month in July. And that's regional configuration with moving nests that are tropical cyclone following. We have the RRFS on the right. That's the Rapid Refresh Forecast System version 1. That's going through last science tests for implementation in March of 2026. The figure there is the smoke prediction from these Canadian wildfires that happen and are happening since last week. Also on the lower left, we have the fact that we have incorporated a number of idealized capabilities that have been released with help from the community. I saw Christiane Jablonowski was here a second ago. She contributed a lot to this capability, and now there's a tropical cyclone idealized capability, so it's not just the operational part that's being developed. And on the lower right, we have the SFS, that's our seasonal forecast system, planned deployment 2028, also fully coupled out to 9-month forecasts. So if you would like to learn more about that, you can attend this workshop that has a very strange name. It's Unifying Innovations in Forecasting Capabilities workshop. It will happen here in the same room in September. It's free, and it's also available for remote participants. Will be in hybrid format. So thank you, and pass it back to Mike.
Well, and so just a few CSM updates from the last year. We've made a handful of beta tags. We're actually calling the model CSM 3.0 now, so beta 1 came out right after the last workshop. We're up to beta 6. I think a year ago we told you that 3.0 is going to be a development release and that 3.1 would be the production release, and that turned out to not be true. So we're planning 3.0 as a production release. Don't really have a timeline. It'll happen eventually. So I asked for updates from the various component models, and so this is a slide from Kate on the addition of a data glacier model. It's a simple way to describe impacts of glaciers on climate. It's similar to the CESM no evolve, but it's better in a few ways. So it's a smaller code base, it runs faster, it can handle surface mass balance and fluxes in a way that's good for CLM. It's very similar to active CESM in what it passes through the coupler, so you don't need to consider it as a special case. It includes this surface mass balance hole filling parallel algorithm, which Kate can tell you all about, and I know nothing about. It's got land ice fluxes that are now, I guess this is a change in the whole CSM model, is that land ice fluxes are now rerouted through the runoff model instead of going directly to the ocean, which just means fewer runoff maps that need to get made as you introduce new grids into the model. Sam put a lot of work into the CTSM documentation, so there's like this whole new system that really simplifies how the documentation is created and how it's pushed to the web. And it includes a whole bunch of new features. It's part of the GitHub workflow. It automatically updates when you change the source code, and you can build the documentation previewed on your local machine. You don't need access to the supercomputer. So when you're home and bored and don't know what to do, you can update the CTSM documentation. A couple of other quick updates. CAM released CAM 7 and dropped the Olarian die core and also the SP CAM configuration. MOM 6 now has support for the BGC tracers in Marble. It's got improved ocean and wave interactions, and there's a new sub-mesoscale parameterization. Cupid is the CSM unified post-processing and diagnostics package. Is now part of the CSM workflow, so you can run notebooks right off the bat. I said it was introduced in beta 6. It might have actually come in beta 5. We're really focused on helping Cecile Hane in running the CSM3 development runs and producing diagnostics off of those. But I think once we get past that, it'll be useful to the wider community as well. I thought I added a slide. Alper and Allison asked me to advertise a workshop. Do you want to just shout out the name and I'll repeat it? It's the correctness and... Okay. Yeah. Okay. So the second workshop on correctness and reproducibility in Earth system models, and I reproduced that title, so I am qualified to go. Awesome. So with that, we'll jump right into the first talk, which is Anne. I'll let you know.
Get into the next.
If you just wait, it'll.
Okay. All right. So, well, my name is Anne. Thanks for the
I'm a little bit shorter. My name is Anne. Thanks for the organizer for accepting ESM team's proposal to come here to update the ESM recent progress and also future roadmap. So hopefully in the next 10 minutes or so, I can kind of remind people a brief overview of ESMF and then talk about some selected change from the last year or so related to CSM, this group, and also possibly talk about future short-term and long-term roadmap. So for those who don't know, ESMF is basically stands for the Earth System Modeling Framework. It is a high-performance parallel software infrastructure using coupled Earth science applications. To promote, let me see if I can use this. Cool. To promote interoperability and usability, ESMF provide the standard model component utilities and also standard definition of state object. And to enable easy coupling of the models, ESMF also provide several methods for regridding. And lastly, ESMF also focus on performance by enabling parallel computing and also resource management. So because of that, a lot of applications uses ESMF as their underlying software. You can see this should look very familiar, CSM. That's why one recent work here. And also UFS, which kind of referenced by Lydia earlier. And there's also other international applications such as NorESM from Norway. And I think the Australia Access is just coming on board. So there are many applications that uses ESMF as an underlying software. So in addition to the ESMF component features, ESM package also provides NUOPSI, which is an optional interface layer that basically make the interoperability and usability simpler. And because of that, a lot of applications elect to also use NUOPSI into their application layer. For example, the CSM. And hopefully this looks familiar. This is the architecture of CSM with a lot of models linked together. Here I highlight with purple background to indicate this is where the ESMF is being used. It's kind of hidden in the background, so I just want to kind of highlight that a lot of the interface layer for each models to wrap around it, the CMAPs and also the CDEP's underlying data models, all supported by ESMF. And because, like every other software development team, ESMF is being used by a lot of applications, the team strive to make improvements and updates to the software. So I would like to take this opportunity to talk about some of the relevant changes to this group from the last year or so. Since I was here last time, I think March 2024. So because of that, let's jump into a selected list of change. So in May of 2024, we push out a patch, 8.6.1, and there are two noticeable changes that may be relevant to this group. One is the improvement of ESMF config class, which make it more robust. And this may be relevant to CSM because you guys are using NUOPSI.run config in your system. And then, sorry, Eric, back. I see Eric right here. So we also accept direct request. Eric was able to caught that bug that helped us update the ESMF mesh, unstructured mesh file so that we can dynamically connect the indexing to an attribute of a variable. So thank you, Eric. Call out. Then in October 2024, we push out 8.7.0. In there, we add a new repeat capability in the ESMF clock, which may be useful in spinning up the model. This is a feature that was actually requested by NASA. They're looping the historical data so that they can spin up the model until it gets into an equilibrium state, and then we can progress with simulation. I kind of call this out because it could provide an alternative for CSM's current mechanism for spinning up and handling of data streams. To use this capability, the user will set a repeat duration as seen here. And then so when the current time, which is represented by this green line, reaches start time plus repeat duration, you will then go back to start time. And then it keep looping until the user stops the looping so that you can proceed with the model. As you can see, go all the way to them. I hope there's some Marvel fans that recognize as Dr. Stranger. In addition to this capability, 8.7 also makes some improvement in the performance optimization. So for example, we have the reduced and regrid rock handle calculation was improved. And for some cases, for NASA, this improvement decreases the route handle calculation time by a factor of 20. We also try to reduce the memory requirement for applications that have a large number of arrays or fields and that runs on large number of pets. And then the third sort of notable change in 8.7 is basically in the new object connection option, we now support a remap method, regrid method, the second order conservatives, and extrapolation method nearest destination, I believe. And I want to use this opportunity to sort of call out that actually ESMF, one of the advantage of using ESMF is that we provide many different type of remapping method. Here's a table summarizing various methods from bilinear to nearest D to S, according to summarize its pros and cons and the typical uses. I'm not going to go through all the text here, but I just want to kind of hammer the fact that, depending on what you want to use, you may want to choose bilinear, which provides a smooth interpolation, versus a nearest source to D, which may provide which copy existing values, so you'll be probably better used for land type of application. So we think that, for me, I'm kind of new to this whole climate science era. So this table is very useful for me. So I'm hoping that this table will be also useful for new scientists, engineers, was they were trying to connecting models together so that they have the right interpolation method for the methods. So we hope to kind of include this table in the new release documentation. Okay, coming back to regular programming. So after 8.7.0 is released, we push out 8.8 in early this year, January 2025. There are two big changes in 8.8. Basically, the first one is performance optimization. This is a deeper improvements such that we basically remodel the state reconcile function. Thanks to Brian Dobbins' team, we're able to kind of do some characterization with this improvement. As you can see in the graph here, we were running CSM3 at 7.5 kilometer global at 65,000 MPI ranks. And then the blue is the older version, 8.7. The red is the newer version, 8.8. The y-axis is basically the amount of time that's needed for initialization of the model. You can see that with the new version improvement, we have about 50%, or less than 50% improvement right here. Okay. Another way to also characterize this improvement is, again, with Brian's help, we're able to run with two different configurations that look at how when the components are spread, distributed across across processor. So on the left picture here is basically the configuration where two components were distributed 75% split throughout different processors. And you can see blue is the old version and the red is the new version, you can see here. As the MPI rank increases, the initialization time for both curve will increase, but fortunately for the new version is increasing at a slower rate, which is great because that means that it doesn't take too much time to kind of to do the simulation. Another notable thing to call is that at 65,000-ish MPI rank, basically the old version will basically crash, and that's why this blue line stopped right there. So with the new version, basically we're able to scale better as the number of MPI increases. The right side graph is basically different configuration where we have a total overlap of 4 components, and you can see that there's a blue line that's just increased quadratically and also crashes around 65,000 MPI. But with the red, which is a new version, which you barely see on the x-axis here, is really right there. It's barely increasing. So to us, it's a huge improvement, at least for this case. Yeah. In addition to the performance optimization, another notable change in 8.8 is the second order remapping of the exchange grid accuracy improvement. And I think this is relevant to CSM because X-grid is now the default for atmosphere ocean flux calculation CSM. So because exchange grid is basically the union of all vertices of the two parent grids, as you see here, atmosphere, ocean in red, and then here's the exchange rate. The benefit to the CSM is that calculations are always done at the highest resolution, and the user is not forced to choose between which grid to compute on. So you're trying to kind of preserve as much as you can. Okay, so because of these two changes, actually the ESM team will recommend that if you have an older ESMF running, it will be best if you can kind of upgrade to 8.8.0. Mainly, most importantly, is because of the performance optimization that we're able to improve. Okay, the team is currently now working on the next release, which is 8.9. We're targeting early July, and there are some potential relevant changes to CSM. So you can see the nearest neighbor reproducibility fix that's called by Sam Robbins. Hopefully we'll fix that, as that means that the calculation result will not change even when the number process changes. There are some new ESMF runtime debugging feature that we would like to push out, so hopefully that will be relevant for scientists, engineers alike, to be able to help troubleshoot some of the issues that they may find. We would like to broaden the complexity of meshes handled by ESM gridding. There are also some requests of ESM Pi feature improvement. This is a Python interface for the ESMF. And this was, I think, requested by NASA, but once we spin this up, it could be relevant to the CSM group as well. And lastly, we want to promote collaborators, and therefore there's some trouble with building ESM documentation from forks, and then we hope that with this change we're able to enable some of the collaborators to be able to build the documentation as well. Okay. So those are short-term sort of role plan. The new, the longer-term role plan, we have a list of things to do. Just to remind people that ESM is being used by a lot of applications, therefore ESM team get a lot of requests and then through the various different channels. And therefore, this is the short list of relevant potential future improvement that for CSM group. So there's additional efficiency improvement. Earlier I had talked about performance optimization. We show some improvement in the initialization time, but we'd like to make more improvement there. There's other direct requests directly from CSMs, as you can see some of the pictures there. There's a signal alarm restart. There's ability to write mesh and convert various grid formats to ESM mesh. Reading shape file into mesh, regridding tool improvements, attaching metadata to ESM object and exchanging metadata through NeoPSI connector. This is a feature that was sort of hidden from other bigger features. So in order for other things to work out, this is actually a stepping stone that we need to get to that. There's multi-language support. Increasingly, people are starting to use different platforms, Julia, C, Fortran. So then this hopefully the ESMF will be able to get multi-language support in there. Merging, field merging, smoothing, blending, and other things that are on our list that we're trying to sort out and prioritize. And therefore, the ESM team is actually planning for a change review board this summer to help prioritize these features so that we can plan out for the next few years. The ESM team, unfortunately, is made up of a small group of people, as you see here. Most of them are here to support me in case people give me very difficult technical questions, which I have no way of how to answer. Therefore, they're right here, stand by. But this team is always eager to answer community questions. We basically people contact us through emails or the GitHub discussion board. But at the same time, notice that there's only 5 of us, and then with me as not really truly an engineer, I don't really contribute to the code. But our time is kind of constrained. So if you're sending us an email, we don't get back to you immediately, please do not despair. We'll get to you. The team is primarily housed within UNCAR CGD lab at Boulder, and then Gerhard is basically part of the Navy Research Lab located in California. Okay, thank you. Any questions? Good. All right.
So if there are questions, there's a microphone in the middle aisle. Oh, I think Leisha's got one, yeah.
You mentioned lots of performance speed ups and, had some plots there about now from the point of view of the user, what kind of simulations can we execute now that we couldn't execute before until you develop this capability? I know there's a lot of interest in high resolution global atmosphere ocean simulations.
That thing. Right now, I know there's some ESM people here can help me, but right now on a high level is the current performance improvement is mostly concentrated on the initialization of the models. And there are other improvement that's needed, which we're planning. I kind of showed there that there's a regret store and whatnot need to be factored in. So we're hoping that we'll be able to get to that with funding. So, but thank you for pointing that out. ESMF has been 20 years in the making. We did a lot of sort of trying to kind of help with the interoperability and the reusability. So we had kind of addressed that. So now we want to focus on the high performance because the community needs that. And so we'd love to get some sort of use case from this group, and that way we can kind of be able to design our solution better. Okay, and then the way to reach us is, again, the email there, and also our GitHub discussion board. That's a new sort of feature we enable, and that's a little bit facilitate a bit better sort of community discussion. Thanks, Lija.
Our next speaker. So.
All right. Is there like a pointer here? Is there like this little one? Point here. All right. All right. So, hi again. This talk is on the progress of expanding the UFS to multiple dynamical cores. This work is in large part funded through the Developmental Testbed Center, DTC, and Dustin Swales from NOAA. GSL is a technical lead. But we also have contributions from other players from NOAA GSL. So I already gave an introduction to the UFS before. So UFS is a community model that's used for research, but it's also the code base from which NOAA draws its operational implementation. On the left hand here, we have a number of operational models that NOAA runs every day in its operational suite, and it's too many, and it's multiple DI cores, multiple code bases, the physics all over the place, multiple workflows. So the idea of the UFS is to work not with NOAA, with the private sector and academia, to simplify this with a number of building blocks from which certain UFS applications can be constructed. So this is, let's say, a work in progress with already some success stories. So one of these revamped models that we have been working on is called the Rapid Refresh Forecast System. And the idea of the RRFS is that it would subsume several others existing production models at NOAA and create like a more simplified, streamlined way of getting products to the end users. So RFS version 1 has been developed over the last couple of years using the FV3 dynamical core as a limited area model. It's hourly updating, meaning hourly doing data simulation and launching a new forecast, uses a 3-kilometer grid spacing over North America. That's this red domain here. 65 vertical levels, uses hybrid 3D ensemble variation data simulation, and also includes the smoke and dust that I showed in my initial intro slide there. So the idea is that this would subsume the HER, Rapid Refresh Forecast System, domains that run in operations, which are listed in blue. Okay, and all that was going very well. We put the model together. The model makes forecasts, but when we started testing this model in the springtime, there was some challenges noticed with the forecast of severe convection. So in this plot here, we have the HER version 4, which is the current operational model, RRFS version 1 in the middle, and the observations from MRMS in the right. And what we see is that the RRFS was making very bulky, broad storms that are unrealistic, and this really got the attention of the NOAA Storm Prediction Center forecasters, who said, well, this is not really how we want to go forward with prediction here. So, and also what we saw comparing the HER with the RFS had very high precipitation bias, especially for high precipitation thresholds. So based on all that, there were recommendations to use the MPAS dynamical core for future versions of RFS version 2. So we've been embarking on building and expanding the UFS to accommodate the MPAS dynamical core. So a little bit about the architecture of the UFS weather model. So the UFS weather model is coupled. So these two boxes here represent the atmosphere, and the other box represents all other potential components like ocean, etc. But for the RRFS, it's atmosphere-only model. So ESMF NUOPSI is used as the coupler mediator between the atmosphere and the other components. Drilling down into the atmosphere, we show here the architecture of the two dynamical cores. So When we started, we only had the FV3, but now we have brought the MPAS as a submodule into the UFS weather model. And we had to do several generalizations because many things were very hardwired to only have one dynamical core. And then the CCPP physics, which is the library of physical parameterizations, is connected with the CCPP framework for auto-generation of caps, which then connect to this green line, which is like an atmospheric driver that calls the dynamics and the physics as the model integrates forward. In a more like top-down kind of architectural view, this is how the UFS weather model works today. So you have a NUOPSI cap on top of the atmospheric component. It calls the ESMF forecast grid, which in itself invokes the FE3 ATM atmosphere driver, which then calls the dynamics and the physics. So we've basically duplicated this structure for now and created equivalents for the MPAS. So the CCPP physics is the same. All the rest are kind of duplicates. And there will be opportunities to do more unification in the future, but for now it's pretty much like a duplicate driver and ESMF forecast grid component. So where we are with this development, I would say like we have a stub capability, because we are now able to initialize and advance the MPAS dynamical core within the UFS weather model, and we can invoke the CCPP physics through the framework, but for now just calling a basic hello world, so we're not yet fully passing variables for actual physics. So a lot of thought, a lot of work has to happen in the physics dynamic coupling, which we're calling P2D here in a few of the slides. In the FE3 dynamical core, the time step starts with calling the dynamical core, and then calling the physics, and then proceeding from there. In the MPAS A, at least the way the MPAS dynamical core is used in the MPAS standalone model, the physics dynamics coupling is different. So the time step starts with calling all the physics except the microphysics, then calling the dynamics to apply those tendencies, but for the microphysics you use the previous time step because you haven't called the microphysics yet, and then you call the microphysics. So due to this different order of physics dynamics coupling, the atmospheric driver has to be kind of rebuilt to accommodate the different orders of calling things. The other thing that is quite different in the physics dynamics coupling is that in the FE3 based model, when you call the physics, those are first called, various physical parameterizations will see the same state, create tendencies, update the state. After that, subsequent parameterizations will always update the state before the next parameterization are called. However, in the MPAS model, the physics dynamics coupling is different. All parameterizations see the same state, return tendencies, and then the state gets updated once. So in order to make the UFS do that, we had to change all CCPP parameterization so they have the ability to return tendencies and do not automatically update the state as some of them do. So now the ability to do time split is controlled by the host model. So the physics itself, the parameterizations, have the ability to all of them return tendencies, and if you want to update the state, you can have the host model control that via nameless variables. So when we do that, when we change from update the state to return tendency and then use the tendency to update the state, the results are slightly different. As Allison would know, now we have to figure out if this is right or wrong. So for now, we're not using a method as sophisticated as others here at NCAR, but what we're doing is just comparing those two ways. So update the state versus return tendencies and then update the state. And we see that in some test simulations, that's not introducing any biases, but when we compute, say, root mean square error of one forecast against the other, we see that the difference starts small but grow as expected. And those are comparable to types of differences that we see when we run the model in different compilers. So so far, so good. No red flags with this update, but more tests will be needed. There's additional work that we will need to get this physics dynamics coupling to work. So there are differences, several types of differences between how the MPAS dynamical core treats the physics when compared to the parameterizations in the CCPP, and those relate to the array layout, Ki versus Ik, to the vertical coordinate that's used, height versus pressure, to the vertical ordering, bottom up versus top down, and to the thermodynamics equations. All these conversions already exist in the MPAS A standalone. So what work that we're doing now is to extract some of these conversions from the MPAS standalone model and plopping them into the new UFS weather model. So in addition to what we're doing, we know that there is more work needed in terms of I/O. And MPAS has parallel I/O, but does not have asynchronous I/O, which we need for the UFS. So we're going to be working with partners to develop a ESMF right grid component, or to connect the one in the UFS to the MPAS. And also we would like to have more work done in the coupling, because even though we're focusing on the RRFS, which is atmosphere only, 3-kilometer short-range weather application, in the long term, we would like to have the ability to run MPAS in the UFS for fully coupled simulations for longer timescales. So meanwhile, while we're getting all this into the UFS, we're also going ahead and doing research with the MPAS A standalone model. So we have updated our physics for this model and have been doing many real-time research runs a day in GSL, sending our model to a number of testbed experiments like hazardous weather testbed, winter weather, hurricane forecast improvement project testbed, and atmospheric rivers testbed. And we are very happy with the results that we have been getting so far, including GSL, NOAA GSL MPAS taking first place here in the hazardous weather testbed, subjective evaluation of high composite reflectivity. So meaning the model is working well for severe weather. This poses a big challenge in how we manage physics, because we're using the MPAS A model, which does not use the CCPP, but eventually we need to translate everything to the UFS weather model, which accesses the CCPP. So this is kind of complicated diagram, but just to say that what we're having to do to deal with this complexity is abstract many of the parameterizations to their own repositories so they can be brought into MPAS A. They're using managed externals to do that, but they can also come into the CCPP as submodules. So by having those standalone repositories as the code base for both CCPP and MPAS A, we hope that when it's time to transition this model from MPAS A to the UFS for operations, it will be relatively seamless. So takeaway messages is that I think we've made quite a bit of progress in terms of getting the MPAS dynamical core into the UFS, having this stub capability now in place. We have a lot of plans on the way forward, and we have secured partial funding. There's a lot of work coming up on physics to dynamics coupling, the I/O, and coupling to the other components. And meanwhile, we are on the MPAS A bandwagon here, and we are trying to put in place lots of strategies to avoid divergence and have our development be synergistic, whether we use MPAS A or the UFS. Time or? Hi.
Curious why you felt the need to reproduce the, call it unusual physics dynamics coupling time loop in MPAS in RFS.
Possibly because that model is working really well. So we've had a lot of experience working with WRF over the years, and it has performed very well for that type of severe weather applications. So that's why we are retaining it. But I think that by having this opportunity to have the physics return the tendencies, it now really opens the door to a lot of experimentation in terms of process split, time split, and how to dribble tendencies, and we're just opening a door for a lot of science.
Standalone in this version in NOAA. Okay.
That's like the reason for this diagram. So right now we don't use the physics that one would get when they just download MPass standalone. We have put our own physics that we lead the development for in GSL. We have integrated that into the MPass. And we're using this strategy to also bring it into the CZPP.
Fine.
Jesse, you're up next.
Okay, cool. Hi, so my name is Jesse Nussbaumer. I'm a software engineer, as it says here at NCAR CGD in the AMP section, the Atmosphere Modeling Group. And I'm here to give an update on SEMA and the CCPP, or at least how we here at NCAR are using it. Before I get started, I want to give a shout out. A lot of people have been involved in this project. I want to specifically call out the core software engineering team I work with a lot. Two of them are on the line, I'm guessing, maybe not, is Haipeng Lin and Michael Waxmansky. I also want to call out two people who are here in the audience, Cheryl Craig and Courtney Peverly, so feel free to make direct eye contact with them later. And so yeah, and then Adam Harrington, who's also here, has been heavily involved in this work. Let's go. So real quick, I'm following the standard science talk outline. So we're going to do with pretty pictures first, then we're going to do important stuff, and then we'll end on pretty stuff so you can forget the important stuff. Okay, so yeah, real quick, if you don't know what SEMA is, it's the System for Integrated Modeling the Atmosphere. And the idea behind it is essentially, NCAR has a lot of different atmosphere models. They're all trying to cover different space and time scales. CAM is kind of the climate scale, and then WACM and WACM-X extend that into places like the ionosphere. Then we have MPass and WRF, which is for the weather scales, and then it kind of goes farther down into smaller, process level scales. So the motivation behind CAM-SEMA was essentially, well, we should create kind of one software framework or ecosystem that can kind of cover all of these different domains and allow for kind of cross-scale science collaborations. And CAM was chosen as a good base since they already had, WACM, WACM-X, CAM, and stuff, and MPass coupled in already. And this diagram shows that, we're going to cover all scales. I should emphasize that the current CAM-SEMA goal is to just cover global processes. That does include weather timescales, but yeah, we're not, right, as of now, we're not going down into things like LES scales. So one of the motivations for this talk is, this is not my figure, and this is kind of old, and you can tell when it started, it was in the mid-2010s, and then they said, by the mid-2020s, we'll be done. And we not quite there yet. So what is the timeline? So I had a really hard time figuring out when SEMA, or was when it called single track, started. I've kind of bounded it. So 4.5 billion years ago, the Earth system forms. And I'm pretty confident it didn't happen before that. Then by sometime before 2018, an actual document come out describing the single track. So it's between those two dates is when single track was created. So most of us didn't really start, a lot of the software engineers who are on SEMA now didn't really start until after 2018, I started in 2019. But I can say that in February 2021 is when the actual CAM-SEMA repo came into existence. So I'd say that was the starting point of SEMA itself as an independent software project. So we plug along, but then we do get a setback. Basically in fall of 2023, we had several major science and software developers who were leading the SEMA leave and going to places like different countries. I remember the time thinking, what could happen in the United States that would make you want to leave here? Anyways, so in 2024, about a year after that, we kind of hit a milestone. We were able to successfully run an idealized physics scheme, a moist baroclinic wave, in the CAM-SEMA framework. This includes the CGBP with both the SE and then actually a little later the MPAS die cores. And so what's the current status? So right now, me and my team are working on bringing in, modifying CAM4, CAM7, and then M-Cubed, working on M-Cube physics to become CCPP compliant. And we'll describe CCPP a little bit later. But that basically allows it to work in CAM-SEMA. Also, ACOM team is bringing in new gas phase chemistry software, both specifically MICM and TUVX, into CAM-SEMA. And ultimately, our hope is to have a real CAM4 configuration running by the end of the fiscal year. Originally, we were also aiming to then have a real CAM7 simulation running shortly after that. But I was explicitly told that we cannot say what's going to happen in the next fiscal year with this project. So just pretend you didn't. Okay, but anyway, enough about the science. So this is a software engineering workshop. So let's talk about what software engineering things have we done. Because I think a lot of people assume that this CAM-SEMA project is just taking CAM and moving it around to CGBPIs and that's it. But we've actually put in a lot of effort to try to improve the software of SEMA relative to CAM. So one major thing we did is change the model configuration. So CAM uses Perl, about 8,000 lines of it, to do all of the model configuration. So all like, sanity checking, generating the name list, making sure your build system's ready to go, all of that. So we replaced all of that in SEMA with Python. We did that for several reasons. One is all of these things interact with SEAM, and SEAM is written in Python, and so integration is much cleaner going from Python to Python than Python to Perl. We have much more thorough testing, which we'll get into later. Right? Python is pretty easy to write unit tests for, and so we've written a bunch of unit tests to try to make sure that our configure system works as expected. But probably the biggest selling point is, I would argue it's more easily understood by users and developers. Particularly scientists, many scientists are now trained in Python. If we run the tutorial, most grad students even come up knowing Python. Very few scientists know Perl. And the other thing is, even if they did, there's a general argument that the syntax of Python is simpler to understand than Perl. If you don't believe me, this is the Perl, and this is Python code doing the exact same thing, which is creating a configure object. And so you can decide which syntax you prefer. All right. So another development we've done is documentation. We've been trying to start off from the beginning in SEMA with documentation, and we've tried to split up into 3 different categories. So the first one is pretty standard, the user's guide. SEMA will need a user's guide, and that's, again, just to describe how to use the model. That's probably not going to be much different than CAM. We'll probably end up stealing Sam Raven's work and putting our name on it. That's pretty straightforward. One thing that we've added, which doesn't exist in CAM, is a developer's guide. And again, credit goes to Courtney and Michael. And most people have something like this, right? Like, how do I open a PR? How do I get that PR accepted? What's the testing workflow? But we also wanted to go beyond that. We kind of wanted to describe the design philosophy of certain things, like what's the workflow we're going through when we build the model, what's the when the model initializes, what's the steps that it's going through, and why is it going through those steps in that order. And the hope, and this already exists for SEMA, and we found that especially for software engineers, this helps a lot understanding the system. Then finally, scientific documentation. I would go ahead and argue that scientific documentation is maybe almost the most important documentation for these kind of scientific models. But they're really hard to write because ultimately software engineers and even technical writers can't write it. They need scientists' input. And for CAM, usually what this happens is right around a CSM release time, scientists go, oh, we should really write scientific documentation. And everyone goes, yeah, we agree. And then we don't do anything until the next CSM release. And so the hope is to kind of lower that barrier we will try to write documentation as we're doing development. And this is actually, we're just copying things that like NOAA and stuff have already done, right? These tools already exist, things like Doxygen. Or this is an example of Ford, which is basically a Fortran specific version of Doxygen. And this, I should give credit to Quanchi Wang, who is a software engineer at M-Cubed, who's been working on this. And the idea being that as we write code and we add comments, if we can try to add scientific documentation, in this case it's converting from potential temperature to temperature, we kind of set up a baseline so then when the scientists do come in to like write the scientific documentation, they have something to start off with. And our hope is to expand this out, right? Right now it's just functions, eventually become full physics parameterizations, and then eventually up through dicores and whole model. And then, yeah, I'll go through this quickly. We're also trying really hard. We found this through CAM4. There's a lot of math that has no documentation at all. There's no citation, no provenance. And so we're trying really hard to track down where some of these equations came from. And ideally, and we try as hard as we can to get a DOI for everything. So, then for testing, we really, in CAM basically has no unit tests, and CAM seems to try really hard to write unit tests that are then run automatically in GitHub whenever you open a PR. Right now we have kind of 3 sets of tests. We have the Python unit test. Remember, the configure code is all written in Python, and that's pretty robust. We have over like 130 tests, something like that. We also have Pylint code that automatically runs on any Python code that's been modified. And then we have Fortran unit tests. And this right now we only have a handful, but since we set up the system, basically every new PR has kind of added 1 or 2 more Fortran unit tests. So we're slowly building that out. And I should emphasize this is on top of the regression tests. Just like CAM, we have a bunch of full system integration tests on derecho, which we've also tried to optimize because in SEMA you can run with just a single physics scheme. So we're also running regression tests with just single physics schemes instead of the entire configuration. Okay, so then this next section, last section, I'm going to talk about the CCPP, which I would argue is an improvement over what we've had in CAM. Just in case, CCPP, the Common Community Physics Package, multi-agency effort designed to create portable and interoperable physics that we can try to share across different host models, different Earth system, climate, and weather models, and allow for scientific experimentation that otherwise wouldn't be possible. So what is this by SEMA? So here's an example of physics parameterization, Rayleigh friction. And on the left is what CAM was originally, and on the right is the CCPPI's version. And the first thought people have when they see this is, oh, you made it worse. It looks so much more complicated in the CCPPI's version. But I'd argue it's not, and it's not in 2 key ways. One is, while the calling structure is simpler, these data structures are CAM specific. So if you wanted to take this Rayleigh friction code and put it in any other model, you would either have to replicate these structures or pull them out or find some way to translate from one to the other, which is a major kind of software engineering burden. These, on the other hand, are all primitive types, and they're all basically variables that every atmospheric model would have, right? Wind, change in wind, change in heating. And so that makes this physics scheme much more portable. The other thing that helps is it also arguably makes it readable. I can just look at this list and get a general sense of what the scheme is doing, right? It's taking in winds, it's calculating the friction, and then giving me the change in the wind and the change in the heating. Whereas this, I have to go farther down into the physics code itself to figure out what's going on. I do want to say that no way, though, does this mean that the framework is anti-object-oriented or anti-data structures. We just want to be really careful. So if we do create an object or a data structure, we want to make sure that it's one that all host models can agree with and easily share. Real quick, I'm just going to hurry up. The other thing that really buys us, which is kind of the original selling point with the framework, was configurability. So what the CCPP provides is a sweet definition file. So essentially it's an XML file that just lists the order of the physics schemes. That makes it really easy to change or swap or anything like that. We ran into this problem in CAM. CAM has a big Fortran code, the phys package, which does all of this, and we learned the hard way that rearranging that can take months and months of effort. The other thing we've also bought, which isn't CCPP specific, but we've done in CAM, is you can now set the number of vertical levels at runtime and the number of advected tracers at runtime, which also means with the new gas phase stuff, you can set the chemistry scheme at runtime. Okay, yeah, so that's it. So here is that animation. And this is provided by Adam Harrington. This is the moist baroclinic wave to prove that I wasn't lying. On the left is Cam SEMA, and on the right is Cam. And you can see that they're basically the same. Okay, cool. I've convinced you. Yeah, thanks everyone. Appreciate it.
Questions for Jesse?
I was wondering if you could talk a little bit about the Fortran unit tests you have on GitHub workflows and what sort of did you need to do anything special to get them to run on the GitHub runners?
And CMake, and we're just right now we're mostly testing. We have codes that are like pure functions that have no use statements, and so those you just can kind of create an easy CMake build and build with them. So those things we're testing now, and we're slowly expanding that out. Like recently, the PIO actually, for example, so we've created this new file IO interface for these physics schemes, and we're using PIO, and PIO provides kind of like its already built environment, so that's also, we can just link to that really easily with CMake. So that's our current strategy. I think as things get more complicated, we might see about bringing in Seam or something. I don't know if that helps, yeah. Yeah, whoever?
Wondering about like high resolution scales like LES. You mentioned some things were dropped, and so what's the plan for that?
I don't know if we have a plan. So I've been told, yeah. I mean, yeah. All I can say is right now, I got an email explicitly saying that right now we're only targeting CAM 4 and SEMA, and we cannot say what kind of happen next because of the funding uncertainty. Again, originally my understanding was the plan was to try to allow for regional configurations and smaller scale. And some we need, like the single column model, CAM single column model. There's a CZPP single column model. But I don't know what the priority is yet. I don't think anyone knows yet.
I mean, is there a long-term plan for how regional configurations fit into SEMA?
So yeah, again, yeah, the focus is, if I had to take a wild guess, my guess would be that if they decide to go forward with that, I know like MPass, for example, now has a regional configuration, so we would probably like go through MPass, have that regional configuration, and then implement the physics, however that might be. That'd be my guess is how we do it. Yeah.
Thanks, Jesse.
Thanks. Cool. Thanks.
Okay. Yeah, awesome. Okay, cool. Hello? There we go. How do we help scientists embrace their inner research software engineer, RSE? So my name is Eric Kluzik, and I work in the land model, and I have a great team that works with CTSM. So let's see, to advance, I push the button. Okay, so this is, I don't have a cool outline, and I don't have an animation like Jesse. We should all be more like Jesse. But what I do have is, here's kind of the problem I've been observing, it's been decades really, is that scientists contribute a ton of code. Oh, does the little fancy thing, I can point at the small screen. So there's scientists that contribute a ton of code. And of course, the model is science, and so that's what we need. And we as software engineers contribute some code, and sometimes we don't interact enough. And sometimes scientists, scientists are untrained in RSE practices, and they need to concentrate on their science, and they don't have time to work on RSE type of things. So how can we increase the collaboration between RSEs and code contributors, the scientists? And this is some things we've been doing about adding lines of collaboration. The goal is to encourage better software development practices from everyone. And, you know, to get this kind of thing where we're working together, there's more collaboration, both sides, and we're teaching some RSE things that are going to help the scientists do their work as well as help us. So, so why should CSM scientists care about the code? So the thing is that CSM is science, but it's expressed in software. So if you touch any CSM code, you are an RSE. So, and you embrace that. That's a good thing. And bad software practices also kill our science. Clean software and software development practices make CSM science easier, more flexible, robust, verifiable, correct, reproducible, all those good things which are important for science. And so how do we encourage scientists to improve their coding practices? And these are some ideas that I have. Help them to see that poor code impacts the science. Oh, where's the button? There it goes. When problems come up, examine the causes and how to prevent it. Point out missing practices that could have helped when you see that. Point out the cost of having poor practices and how that's greater than the cost of having good practices. So here's an example of this, and I'll talk about this a little bit later. But we have a scientist, Adriana Foster, who also lovingly embraces her research software engineer and did some work where she looked at a subroutine and noticed a weird behavior that is going to have a science impact. And so, you know, doing kind of RSE unit testing kind of thing helped improve the science. So, so what does work? I think I got this in the wrong order. Okay, what does work? Demonstrate costs, demonstrate practices, educate on practices, and work with people with the highest interest in RSE work. How do we encourage scientists to improve coding practices? I'm kind of repeating myself, aren't I? But RSE team, so one thing we need is that we as the RSE team need to be actively doing and experts in these practices. We need to have education resources available, tutorials, documentation, etc. I'm also convinced that we need to use metaphor and non-technical terms to communicate better. Encourage people that try and provide them help. And education on those practices need to continue to be done. You're never done at doing that. We probably only can introduce one practice at a time and make the most important things easy. And these things in the red are the things that are realized we need to be doing and we're not actually doing right now. So these are all the things that I came up with that I noticed do not work in a community model, in, you know, like demanding that scientists do whatever, shaming, claiming, all kinds of things just doesn't work. So, but let me get back to the point of what makes doing RSE type tasks hard, and this is really doing any kind of coding in CSM. And, you know, what can we learn from the software engineering industry? So debugging is the most expensive thing we do. It's inherently intractable. It's not possible to estimate. The further along in the development, the more expensive it is. And if you have brittle, poorly designed, poorly tested code, it keeps you constantly debugging. So it keeps you in, I call this debugging hell, and none of us want to live in debugging hell. Although some of us have to live there, but let's try to avoid that as much as we can. So we looked at this with our team. What are the problems debugging poor code? And it looks like half of my time is spent in debugging hell. In our team, it was kind of, they thought it was around 20%. And so, you know, one thing you can do with that is you can identify problems with the code. and refactor to improve the code that's problematic. For that's commonly changed, problematic enough, that sort of thing. And so what practices does the software engineering industry show that helps? And there's 3 things I'm going to give here. And one is requirements. Reduce the set of things that you need to do to as small as possible, not too much nor too little. And spend effort into the design of the code itself. Again, brittle code, poorly designed code is hard to work with. Add automated testing while you develop, test-driven development. So, and the thing is untested code is broken or it's going to get broken. So don't add untested code and continue to run your test suites because it can get broken later. And so these are some list of RSE suggestions that I came up with, and I presented it to the CTSM scientist. And the thing is, all of these things are great, but it's too much. I realized it's too much, and so I kind of need to, present one thing at a time. So what are some things we're trying? So we're trying a thing called parallel work sessions in CTSM, which hopefully will mix research software engineers and scientists, and there's also hackathons that happen, which are great in getting that collaboration going. We made it easier for scientists to add stuff to CTSM because we have this bit-for-bit development branch, and so more people can contribute to the code easily. We're giving scientists a stable development version with our minor version updates. And with that, we realize we're freer to bring in small updates on main dev, which can include hot fixes. We've been doing Python unit testing, and that's like a standard now, and that's really great. And I think Jesse said this, that Python is really slick with their unit testing. We're educating more people on our PF unit-based Fortran unit testing. And there's scientists using Fortran functional testing, which I'll talk about a little bit more later. And then I have a survey, and I'd like everybody to take my survey, everybody here, as well as everybody that you see at this conference. So PF unit testing for Fortran code. Again, we've had it in place for a long time. I'm convinced that it's something we need to do more of. I was able to teach Keith Olson, who's a scientist, to do this, and he was able to figure it out, and he sees the point, and he'll do it again. So I'm hoping I can teach more scientists about how to do this. So functional unit testing, this is something that Adriana Foster has developed, which is kind of a unit testing framework to build drivers for science subroutines. It includes NetCDF input and output and Python plotting. And she's been teaching this methodology to some other people as well. And it includes people like Linnea. And she's using this for faster development of a machine learning parameterization. You don't have to go in the job queues, you run reactively, the builds and the runs faster, input and output is simpler. It's just accelerating what she can do. So that's awesome. And then again, here's the example of the behavior. She's looking at behavior of passing it a science subroutine, input, and then plotting plotting the results and comparing it for different things. And sometimes it points out some bad behavior, which is great. So we're hoping to do more of that. And again, here's my survey. I'd like everyone to take it. And questions. So, and I can't just have you ask me questions, but I have questions for you, because I'm still wondering, how do we encourage scientists working on the code to improve their development practices, and if we're working on that, how do we measure success? So, love to hear answers. if we have them, and love to hear questions. Yes. Questions or answers? Yes. Okay. Yeah.
I'm really happy to see this talk because I've been involved with similar efforts in GSL for many years. And I have found that the idea, convincing people that the cost of the practices is smaller than the cost of not doing the practices, it proves to be a very, very hard sell. And, you know, the theory is that by doing these practices, eventually you just demonstrate that that's the case. But I've found that even management won't back you up when it comes down to a trade-off between, do we meet this deadline by not following the practices and deliver this product that we promised by this date? Or, you know, do we do that, or do we violate the practices? And I'll tell you, meeting that deadline wins every time, hands down.
Yeah, yeah. Yeah, I think one of the things I'm trying to do is that when we have because there's the debugging hell thing I was talking about, and the thing is that, you know, throws a wrench in everything, and it throws a wrench in deadlines and everything else. And so when that comes up, I try to say, you know, if we had done this practice, we'd have been less likely to run into this problem, or it would have been a lot simpler, you know. So some work that I've done that, you know, takes a month, you know, could have taken, you know, a week at most if we had better testing in place, for example. So I've been trying to do that kind of thing. So, yeah, but yeah, I mean, that's a good point. Yeah.
Sell it to management is when deadlines get missed because bad practices led to a delay, which has happened.
Cool. Thank you.
Okay. So we have one more in-person talk, and that's Chris Harrop, and then we'll have an online talk before the discussion.
Okay, that's interesting. How do we get... Oh, all right, good. So I'm going to talk to you a little bit about a federated workflow system that we're developing called Chiltepin. And before I get started, I just want to make sure to acknowledge our funding from the SENA program at NOAA and our collaborators at the University of Chicago and Parallel Works. And I'm going to give you basically an introduction to federated workflows, a little preview of what Chiltepin looks like currently, and just end with some challenges in future work. So I'd like to start with pointing out this paper by Peter Bauer, which you may or may not have seen. It came out at the very end of last year, talking about numerical weather prediction being at a crossroads. And the reason I bring this up is because it lays out in a perfect way the motivation for why we're doing this work on federated workflows. Essentially, he makes the argument that the way that we're doing development in NWP with the increasing requirements for increasing complexity of the modeling, there's no sustainable way for any single weather center to continue to provide the high performance computing power required to meet the needs of this. And he points out that, you know, one way out of this mess is the incorporation of machine learning and AI, which is much faster, so we can get some of that computing power back. But there's really, it's kind of an untenable situation. And so the idea is that going forward, in order to sustain this effort in continuing to improve weather forecasts and Earth system modeling with increasing fidelity and accuracy, we need to be able to actually create collaborations among multiple institutions that don't normally work together and harness computing power that's spread across different sites or and managed by different people. So if you're familiar with weather workflow management in general, one of the problems that you're likely familiar with is the large proliferation of workflow management systems. This is a common problem in workflow management, and it's also happening in our area of study as well. As you can see here, there's a number of workflow systems that have been developed specifically for numerical weather prediction and Earth system modeling. And the reason why I list this here is because I wanted to show why we're developing a new system. And the reason is that although all of these systems have comparable capabilities and they have various strengths and weaknesses, and some of them can harness computing power across different systems, they do this in a distributed fashion. It's not really a federated workflow system. So I'll get to that in just a second. So I found that there is often a lot of confusion about federated workflow systems. What does that actually mean? So I'm going to go into that a little bit here and sort of try to distinguish it from a distributed workflow system. So a federated workflow system is different. And the reason it's different is because it provides you a user who has some identity, and this user has logins on various systems. And these systems may belong to different institutions that don't work together. It's different bureaus of the government, universities, and so on and so forth. But what you can do is you can have a so-called federated identity. So this person has their identity, and they want to access all of these systems. And to do that in a federated fashion, you have to have a identity management. So you have to be able to log into this, to something, to get, to verify your identity. And what happens is you get these tokens back. These tokens verify who you are and what you're allowed to do. And then when you want to access a system, you present these tokens, and you're either allowed to do the action that you wanted or you're denied. And by doing this, you're not relying on very fragile SSH tunnels, and you're not relying on a connection to be up. You can use these, you can take your identity, link it, your federated identity, link it to the identities of all the various systems you want to access, and and all of the access can be controlled and limited in scope, and you can reuse these credentials until they expire, and thereby you have sort of secure access across a whole set of autonomous resources that without having to maintain all these weird networking pipes and things like this. Okay, so what we need is a way to implement those clouds, a way to verify the IDs and handle all of the ID management. And the solution that we are using is Globus. So most of you are probably familiar with Globus as a way of moving data around between different systems. The Globus is actually a lot more, there's a lot more to Globus than that. So Globus, behind the main thing that allows you to do those data transfers is its ID management capabilities. This is actually a very complicated and difficult problem to solve, which is one reason why I didn't want to do it myself. So it's good that we have Globus to do that. But Globus also provides, in addition to its data transfer service, it provides a function as a service compute platform for serving compute. So what you can do is you can create compute endpoints on different systems with Globus. And then you can access these endpoints and run things at these endpoints by logging in with your federated identity and submitting functions, and they just run on resources that are acquired by Globus. So Chiltepin, the system that we're developing, uses Globus to handle that piece and makes life much easier. So the next thing that we need is a way to sort of handle all of the orchestration of all the different tasks and things. So Globus gives us the ID management and creation of the endpoints and remote execution of functions. And then there's another system called Parcel, which is a Python-based workflow system that's integrated into Globus. Globus uses Parcel, which is the reason why we chose to work with Parcel here. So Parcel allows you to create a Python program that is itself a workflow. And with Parcel's Globus Compute Executor, you can create a program that submits your functions to all of these remote locations. And it will orchestrate and keep track of everything, enforce all the dependencies for you. And so we are using the software development kit for part of Globus to log into that, and Parcel to manage the execution of the workflow. Okay. So the overall vision is that users will use Chiltepin to create Globus compute endpoints at whatever systems they want to use, whether they're on-prem HPCs or in the cloud. And then will, from wherever they sit, it could be on their laptop, it could be on another HPC system, it could be anywhere, run their Python program. The Python program automatically deploys these tasks to the compute endpoints where you have requested their execution to run, and orchestrates, it keeps track of all of the dependencies, tracks the failures, retries, all that sort of stuff. And you're able to take advantage of all of these different systems. So what you can do is you can now design workflows that span multiple systems, and you can deploy different parts of your workflow to different resources so that they run on the resources that are most effective. So for example, with machine learning coming into play, we now have physics-based models, we've got machine learning, there's a lot of different requirements. Some things may need just your typical CPU stuff, some parts might want a really high-powered GPU. All these things may be located in different places. There could be different disks, different storage, different file systems that need to be accessed in different places. The point is that you can deploy each part of your workflow to the system on which it's best suited. Okay, so I'm going to do something that you're never supposed to do in a talk, which is show some code and stuff. But just to give you kind of a little flavor of what this might look like. So Chiltepin gives you compute endpoint lifecycle management. So it's got a little command line interface where you can configure and start endpoints. So this is just kind of what it looks like. You create it, you just log into the system you want to make the endpoint on, you configure it, you start it, and then it gives you back this UUID, which you can then use to access it. So this sort of is meant to illustrate a little bit of what a workflow might actually look like in a Python program. On the left-hand side, there's a class, MPass, and there's these decorators, bash task and Python task. Those decorators automatically turn that function into a workflow task. And so if you call that function, it will automatically run that function on the resource that you specify. And the way that it does this is when it sends it to Globus Compute, Globus Compute will actually start up a job on that system, acquire the resources, and then run your task inside of that job. So on the right-hand side is just an illustration of how you might call these things. So when you call these, the functions return immediately, and they give you back a future, which represents the eventual result of that computation on that remote system. And then you can take that future and you can inject it into the parameter when you call the next function. So in this case, MPass init, I get that back right away. And then I call MPass forecast, which needs to run after MPass init has finished, but I give it the future as a parameter, which tells it that that's a dependency. And then that's how the workflow works. And then you can see I have these executors. I'm pointing on the screen here. It's kind of funny. How does that work? Okay, these executors that specify where that is supposed to run. At the moment, we're actually don't have anything to automatically have it go to, to choose a system that to run on, but eventually we would like to do that. All right. So a little bit about configuration. So you have to specify a configuration that describes the resources that you want to use. So in this case, we have a resource called Hercules, and you can give it a bunch of environment that tells, what basic environment setup that's required in order to use this resource, the endpoint ID, and then a little bit about how the resources are acquired. In this case, it's using Slurm and uses srun for its MPI launcher and some node configuration stuff. So that's normally you would have a number of these blocks for each resource, and you would just call them as needed. All right. So challenges in future work. So one of the challenges that we have is that we're not really used to workflows as Python programs. Usually we have a sort of a static description of a workflow in a YAML or an XML kind of format. And then there's another separate thing that's an engine that will read that in and then execute that. But in this case, what we have is we actually have a Python program that itself is the workflow. And if the workflow fails and you rerun it, it will remember what it already did and it will skip over the things. But it's a little bit of a different paradigm. One of the things we need to do is to develop good monitoring tools. Parcel does have access to monitoring stuff, but we just haven't had a chance to develop really sophisticated tools for it yet to track, so that we can give users a good way of tracking the progress of the workflow. And similar with the built-in failure recovery that they have. And then the other thing is as the developer of Rakoto, one of the next things on the plate is to actually have this thing have support for legacy Rakoto workflows, so that it can actually read in a Rakoto XML and run it. And then, of course, continue to build this so that we have a sustainable workflow future, because without federated workflows, you're not going to be able to sustain the modeling efforts that you need to do.
In your example, and maybe it was just a contrived example, but you were doing the initialization on one machine and then the run on another. Is there a mechanism to get the data that you've produced in the initialization over to the other system?
There is. It's just there's actually a built-in workflow task for transferring data. That was kind of an example so that I could illustrate how you would do multiple systems, but it's an unrealistic example. So there is challenges in the data management, because the whole idea historically has been move the computation to where the data is, because moving the data is really expensive. But when sometimes you have to do both, and it's sort of sometimes it can't be avoided. But
can you stay for the discussion now? Because we're behind. We'll have time in the West, 20 minutes. And then is Phil online? Are we?
Yeah, can you hear me?
We can hear you. If you give us just a minute to get your talk on the screen.
Yeah.
Yeah, and we're ready for you to go.
Perfect. Yeah. Hey, everyone. I'm Philip. I'm one of the developers for the UX Array Python package. I work on the GeoCat team at NCAR. So today I'll be going over some recent updates and developments for UX Array. So for those of you that are not familiar of what is UX Array, we are an open source Python package that provides unstructured grid data analysis and visualization functionality for climate model outputs. So from CESM, MPAS, all of these different models. And our design is heavily inspired by X-Array. So we extend that package to provide a very similar workflow while providing unstructured grid-aware functionality. And we use packages from the scientific Python ecosystem, so notably Dask, Numba, and Datashader to accelerate our functions and to provide support for kilometer scale resolutions. So let me quickly go over what the UGrid conventions are, because this is what our package is based upon. So on your screen, I'm going to share just a couple grid formats. You may be able to recognize what they are, but for the sake of this presentation, it doesn't actually matter. What's important is that UX Array can read in these formats, whether it's from MPAS, ESMF, ICON, ChemSC, all of these different model outputs. With UX Array, we have a specific data ingestion step that can determine what grid format you're working with and encode them in the UGrid conventions, which this is a standard for representing unstructured grid variables, topology, connectivity information according to the CF conventions. So the main benefit to this is instead of needing to write separate analysis functions for different grid formats, it's a single tool that can be reproducible and operate on any supported grid format. And to go over some of the core classes that are part of our design, the first one is our grid class. And this is what we use to store our unstructured grid information. So this can be coordinates, connectivity, face areas, different descriptor variables that are used to represent the underlying topology of your grid. We then have a UX data array, which this represents a single data variable that resides on an unstructured grid, and it is linked to a UX grid. So the main difference compared to an X-array data array is that it's attached to that grid object, and you know what source grid you're working with throughout the life cycle of any operation that you're doing. And then similarly, a UX data set takes things a step further. It's just a collection of data arrays, all of which are assumed to reside on the same unstructured grid. And then very generally going over our overall design, I already covered our grid, data set, and data array classes, and you can see how everything flows right here. So we support those grid formats that are listed above. In addition to outputs from climate models, you can load in point data, you can have custom topology. We have a lot of flexibility in that regard. And then all of our plotting, regridding, computational operators, all are directly part of these custom classes that we've wrote. And the intention of this is to allow the user to transition their existing structured grid workflows to unstructured with minimal code changes. So let's look at a basic example. Here on the left, we just have 4 lines of X-array code. We're loading in a data set, opening it, and then plotting a data variable. Relatively straightforward. With UX Array, there's really just a couple changes here. We use the UX Array package instead of X Array. You need to specify your grid and data path because we need to be able to interpret what source grid your data is on, and then all the other syntax is identical. And these plots look different. I did some very basic regridding for the left one, so it's not a apples to apples comparison, but the one on the right is your original unstructured data. The one on the left is just some dummy data for the presentation. And let's go over our toolkit of functionality. So we have an extensive set of visualization functions, both vector and raster based ones, and there's a few examples here. And these are written around the hollow views and data shader packages. So it was our intention to allow the users to visualize the highest of resolution grids with without needing to worry about performance. And we are also currently working on some custom sampling techniques to enable native matplotlib workflows, which we know has been requested by the community. And let's look at some of these plots. So this was a 3.75 kilometer MPAS model run. And with by using data shader and hollow views, you can interactively zoom in to a region of interest. And if, for example, you're on a multi-core machine, it can dynamically in parallel re-rasterize as you zoom in, so that at a global scale, you may have your output image looks much coarser, but as you zoom in interactively, it dynamically re-renders your image. And this is all done automatically because of data shader. Let's go over some of our other functionality that we support. So I know in a few other talks there was some notes about regridding. We support a very basic set of pure Python implementations for, this is for subsetting, sorry. For subsetting, here we allow the user to quickly select and restrict the domain of their data using an Xarray-like interface. So couple snippets here. We support bounding circle, bounding box, and nearest neighbor based approaches for selecting your data. Let's see, we also support cross sections. So if you're working with trying to get all the data at a line of constant latitude, constant longitude, or between intervals of either, we also support that functionality. And everything is contained in a fluent interface. So the output of a cross section will be a brand new data array that is attached to a brand new grid that is restricted to whatever output variables you have. So we try to keep everything self-contained and working in a fluent manner, which again is consistent with how Xarray and other Python packages do things. And then I was a little ahead of myself on the previous slide. For remapping, we support a very basic set of remapping functionalities that are written in Python. So there's no need to depend on any larger external libraries. Because of that, our implementation is definitely limited compared to a lot of others, but for quick remapping, we support nearest neighbor, inverse distance weighted, and bilinear approaches, all directly contained within the package, and we do accelerate it using some data structures from SciPy and by using Numba wherever we can to get as much performance as we can. And then another summary of some of our other analysis operators. So we support zonal averaging, different types of unweighted and weighted averages, also topological aggregations and geometry routines. Again, as I've mentioned, we try to use Numba as much as we can for these core grid routines to squeeze out as much performance as we can in areas where Dask or other packages are don't really work with our existing workflows. And in addition to that, we are working with our SciParts intern more advanced vector calc. They're all in the works. And now let's take a step back and look at some more community resources and documentation. So as I mentioned, UXRay is completely open source. If you're interested in contributing or just taking a look at our code, there is a QR code for our public repository. And we also have an extensive documentation page, including a user guide, gallery, also contributors guide, and other pages. In addition to that, outside of our primary documentation, we have developed 2 cookbooks, which you may have seen these before if you've been following any of the UXRay development. We have both an unstructured grid visualization cookbook and a HealPix cookbook. So with the UXRay team, we're always looking for opportunities to enhance our community collaboration, and documentation in Project Pythia is one avenue that we use. And to summarize, so UXRay, it's a Python package that enables the analysis of unstructured grids from mostly climate model outputs and not just from formats that are produced by CESM. If you have MPAS models or some of the European models, we provide these lightweight ingestion layers where as long as we can load in your data and represent it in the UGrid conventions, you can take advantage of all of our analysis and visualization functionality. And much of it, we try to support kilometer scale grids and higher resolution models by leveraging packages like Numba and Dask. So I'll leave it for questions. I think we're right on time as well.
Thanks a lot for this. This is UX Array seems like a really great package, and appreciate your presentation on this. I'm curious, the capabilities for UX Array to work with structured grids, and if I wanted to write like a generic, some generic Python code that could work on either structured or unstructured grids, would it make sense to just use UX Array, or would there be friction in using UX Array for structured grids compared with just using X Array?
The main concern would be the way we represent structured grids. Because of the UGrid conventions, which our package is based on, we need to on the fly generate things such as your face to node connectivity, which isn't technically required if you're just doing a pure structured grid workflow. But for the sake of just having one grid that's structured, one grid that's unstructured, you should be able to use UX Array. I would still suggest probably pure X-Array workflows would work better just for standard structured grids. And we have designed the package to be as close to X-Array as possible. So under the hood, a UX data array still inherits from X-Array. So they're both related, just UX Array extends and builds upon what X-Array already provides. Thank you for the question.
Thanks again, and we'll switch to the discussion session. So to seed the discussion, we have a slide with like 5 possible questions you might already be thinking of, or you can use this time to ask questions of the speakers. So I think Ufuk, if you want to start by asking Chris your question, that would be.
About this new workflow tool, are you providing some way to reproduce your workflow? Are you storing some provenance information or metadata related with the workflow itself? Because some user can run the workflow in some machine with some compiler, but others will run another compiler and another machine. They will end up with different results maybe. So is there any way to replicate exactly the same workflow by sharing something? I don't know.
Yeah, I'm sorry. I can't believe I forgot to put provenance on the future work. But yeah, that's a very critical part of any workflow system is provenance, keeping track of how to do it again. Since it's a Python program, I'm wondering how that's going to work. I'll have to think about that.
So some potential questions to think about. Brian Dobbins had asked us to put this bullet about, like, how do we fund CSM software given proposed cuts to NSF and the NCAR base funds? I think tomorrow there's a cross-working group session on variable resolution and high resolution models, and that's going to be very science focused. But I was kind of pushing for that event to happen because I think in this room we need to think about how the different components are going to interact with these new capabilities and trying to think of ways to be consistent across components instead of everybody doing it themselves in different ways, or whoever does it first gets to dictate how everybody else does it. Well, what can we do to strengthen collaborations between CSM and modeling groups or between NCAR and other institutions? This might not be a great discussion point, but something to think about and talk to Legia and I about is for the next winter working group. Like, I thought the hackathon went well. We only had a day because we came up with the idea of doing a hackathon after we thought a day would be more than enough talks. So do we want a 2-day hackathon? Do we want some talks and some hacking time? Or anything else you want to talk about? So we have 15 more minutes. The microphone's open. I'm taking notes on who's talking.
I just mostly want to keep Mike happy. And I wanted to say thank you, Eric, for your talk. Like, that's really what I got up here, because I kept wanting to say, like, that was a really good talk and very thoughtful about how to do this. I work with a smaller set of scientists in the land ice group, but we're sort of trying to push them towards a lot of those things. And Bill Sachs told me about a testing script that you developed to run the CESM test more simply, which is super helpful. So I'm just wondering, like, you know, if there's a way we could incorporate more of that sharing throughout the software engineering groups that we do, so that other groups could learn useful ways to improve RSE stuff in their groups. Also, I vote for 2 days of hackathon, and I don't know the answer to the other questions.
I wanted to ask, I think if you heard the Earthworks talk yesterday, they pointed out problems that we found in ESMF and PIO at very high processor counts where we frankly never test. And, you know, is there a way to reproduce those high processor count capabilities at, you know, small processor counts?
Hey, Brian, did you hear that? Yeah.
On testing is that when you write tests, they test exactly what you tell them to test. And these sorts of scales, because they require lots of resources, we can't do it via GitHub Actions. I'm not going to get a 2.4 billion cell mesh there. And this is more of a communication issue with, you know, people here know I've bugged the directorate. I'm like, you want to run these bigger things, we need bigger systems, and we need bigger allocations of time. So this is a communication issue. I don't see a technical way around this. Like, it's a question of, even with testing, like, do you write a test that takes 90% of your yearly allocation that you're gonna, you know, that only occurs in one instance? So we do want more testing. We just have to be smart about the testing we do, and we have to realize you're never going to cover all the areas. You cover what is most important. So that's the important thing to me. That and communicating that, again, as we push into these regimes, we need more resources, people and systems. So yeah.
That reminds me, test coverage tools are really helpful in figuring out how good your testing is.
On this testing train, I just want to, and maybe we'll talk about it at the correctness workshop, so we don't have to bring it up here. But one thing I've struggled with is what makes a good test, because like we have tests for things like here's some function, and yeah, like I throw in numbers and it gives me a correct number out, but that feels like I'm just testing, yeah, the compiler successfully divides two numbers. It doesn't feel like a very meaningful test. And so I'm kind of curious what other folks do to, like, how do you decide this is a good test or a bad test? Think about it. I think.
Yeah, on that, I mean, it might not seem dramatic when you write tests and they all work. For me, that would be, I would take the rest of the day off. That would be amazing. But it more becomes useful when things start to break, right? And so, like, it's not really necessarily a compiler thing, but like adding in sort of edge cases, like what if you put all zeros into this? What if you put a negative number into this? Is the error handled correctly? And PF unit, unfortunately, can't really test like correct error handling at least, but yeah, it's sort of weird edge cases that are potentially the most useful.
Yeah, and that reminds me, testing the happy path is what most people usually do, but it's also really good to test the unhappy path. Test to make sure that when things go wrong, they're going wrong in the correct way, or that you're catching them correctly.
I'll also talk a little bit more about my philosophy on testing. We have to be careful because, again, getting to the resource issue, like there are lots of things we can test. Our code has so many degrees of freedom. And the question is, every time you write a test, you have to maintain that test now. And so the question is, if you're writing infrastructure code, like I think of it, if I'm a bank and I'm taking an account number, I want to check that no number was given to me. I want to check that I was given a string or a buffer overflow, stuff like that. If I'm writing something that takes in a 3D field, I can assume the people passing in it are sending in a 3D field and not a text string of, you know, a quote from the Bible or something like that. You know, you don't have to go to extremes, because then you have to maintain a lot of extra tests. So it's always a balance. So we think about it. And I think balance is maybe, I feel bad. Somebody was talking about like before, like management always has a different opinion. And I'm wearing both the software hat and the management hat and trying to balance things here. But I think it's important that we think about what we're trying to test, and we never, I don't know anybody in this room who has enough time to do all the things on their plate, and the same is true with testing. So think about what we really want to achieve and write tests for that. If it's code that changes often, maybe we don't write tests for that much. We do statistical tests. This is one of the things we're moving to for our physics. If it's infrastructure code where you are adding you know, numbers together and you want to sum, well, hey, that you can do pretty easily. But it's more about not testing everything, testing what is important to test and being smart about it. It's a really great conversation, because I know there's a lot of different thoughts on testing and a lot of different ideas, and I'm by no means an expert, but again, that's the manager hat, being like, I'd love to have 418 tests for my Hello World program that takes a string, make sure it's not Unicode, make sure I can write to the file system, make sure, you know, all these things, but that's not a good use of time. So it's a balance, yeah.
So getting back to what Kate was talking about, a couple of things there. So I like the idea of a 2-day hackathon, so that's my vote. And then Kate was talking about, you know, getting us together and talking about how we're doing things, and I really love that idea. I don't know what that would look like necessarily. Maybe that's a hackathon, yeah. Maybe that is. Maybe that could be part of one of those days or something. Just how is everybody doing unit testing or whatever thing, and then we talk about how it's done and learn from each other. So maybe that's an idea. Let's see, and then testing. I think the code that gets changed is probably the code that needs to have the most testing on it, which I think, I'm not sure if Brian was saying that or not quite, but he's got a good point that if it gets changed a lot, then you can't just check for an exact answer. But you can check for behavior. Is it monotone increasing, or, you know, whatever kind of characteristics it should maintain to have. Martin Clark had this thing about, he called them laugh tests, which were kind of basic things of making sure you're conserving mass, or, you know, simple kind of things, which I think we should do more of that as well. That would be more testing. The science behavior is what it should be. So that's another thing we can do. So anyway.
I'll maybe just add to and like amplify some of these points. I think just building on Eric and Kate's discussion and some of the points here, I think you know, you mentioned my consistency across components in the variable res and regional setup, and I think, you know, the more that we can work just in general to have I think uniformity across the different model components, rather than in ways that make sense, you know, in places where we just have like arbitrary differences. And I think like the testing, you know, testing setups is a big one. Like each component of CESM has slightly different workflows for how we do testing, and it's kind of arbitrary differences that don't, I think, have good reason. And I think we'd gain a lot from learning from each other, and also gain a lot in terms of just the ability to for software engineers to move more fluidly from one component to another if we develop more of that uniformity. And I think the more you know, one way to get to that hackathons is a good idea, but also just like if we had a little more culture of like sitting down with each other and, you know, for an hour or two kind of pairing and working on some problem together and seeing, oh, you do it this way. Oh, I wonder what's different from my workflow. And And then just my thoughts on the testing piece. Yeah, I think, just to add a little bit to what Brian said and like amplify that, I think there's a good question that was posed to me at one point was like, when you're writing this test, are you actually worried that there's a chance that it's going to fail? Because sometimes it is easy to like go off and just like, oh, I want to test this case and this case and this case. But if you don't think that there's actually really a chance that your test is going to fail, that's the point at which you say, okay, maybe I've reached diminishing returns. But the other point on that is, for me anyway, a lot of the value in testing comes when you're doing it alongside the development, and it replaces the kind of manual testing you'd otherwise be doing, and that's where you really get the bang for the buck. And it's something I've struggled with that is, and so we're posing like a challenge rather than anything that I have a solution to is when we get science code, I think the value would have come in the testing if the scientist had written the tests along with doing that development, rather than presumably spending a lot of time manually testing and not having tests that are kind of developed as an artifact. But in my experience, like writing the unit tests can be a lot harder than actually writing the code. And so how do we actually get testing good tests out of that from people that haven't spent years developing that kind of unit test writing, those unit test writing skills? I've struggled with that.
We're 3 minutes away from break, which is about, I don't know, many more minutes than I thought we'd get out of the discussion. So good job, everybody. Thank you. Jesse, did you want to say, were you about to get up? No, say it. Right. We'll have 2 more comments. We'll have you and then Kevin. Yeah.
Conversation, so I won't. But I guess first off, I also vote for a 2-day hackathon. So keep me on your good side when I ask for Cupid questions. But the other thing, which kind of going back to Eric's talk, and one thing I've kind of struggled with is we want scientists to know more software engineering, but at what point do you draw a line and say like, no, this is knowledge that I just don't expect you to necessarily have. Like an example I can come up with is Git. So like obviously we want our scientists to know basic Git flows, like how to make a PR or whatever. But at some point, I don't want them to be doing like interactive rebasing and then coming to me because their ref log's messed up or whatever. So at what point do we say like, no, this is our kind of like area of expertise and we don't expect you to. I don't have an answer to that, but if anyone has opinions, that would be great. Yeah, thanks.
Very quick plea or request that if you do go to the trouble of making a test, try to print out a number that is going wrong. Because if there's just a message that the subroutine failed, then somebody has to go in and add some code and run it again and figure out what number they're trying to fix. So whenever possible, print out a number.
Okay. We did it, team. We made it to break. Good job. So just a reminder, there is a happy hour at Rayback about 5:30 tomorrow. Hope to see you all there. Yeah, so there's something running here late, and so we can't do it tonight, but tomorrow. Cool. All right. Thanks, everyone.